Good afternoon. Can you hear me?
Yes.
Everything okay? Okay. We are going to start this first session of the second day of the conference. We have three presentations in this panel, and also some time for discussion. The first presentation is titled Potential Impact of Incremental Innovations on Price Reduction. And it will be presented by Dr. Luis Crespo, who is president of the Spanish Solar Thermal Electricity Association. He is very well known in the field of concentrated solar thermal technologies. You can find a very short CV in the web, so I won't go into the details. I prefer to give the time for the presentations and the discussion. So, Luis, the floor is yours.
Yeah, yeah. Good afternoon, everyone. How I can share my screen, because I don't see any possibility in the.
You will be given a button.
Yeah. I think you already have it.
I already have it. How share a screen? What is the? Yeah, here, mostrar pantalla, right?
Okay.
Can you share my screen now?
Yes. Yes, we can see it.
You can, yeah. Okay, so can I start now? All right. Yeah. Okay. Well, thank you very much, the organizers and the Cyprus Institute, for providing me this opportunity. And I am, as most of you know, if you are following Solar Places and other congresses, well, I am just at the end of my professional life, and this is a kind of legacy I would like to share with all of you. Just, sharing some ideas, which are, some of them are obvious, but I think, in my opinion, could present a right path for going a step forward in reducing prices for CSP plants in the next generation, which are about to happen, at least in Spain in a few months. We hope that we will start with new projects. So, first of all, I would like just to give a kind of introductory reflections, and I think it's obvious. I mean, for everybody, the context is that price reduction is a must. Energy transition is quickly happening everywhere. There are only few countries where thoroughly planning exercises has been done, especially in the European Union. So the member states of the European Union has already presented the so-called national energy and climate plans, showing which are for them the views and the contributions of each of the technologies, of renewable technologies, by 2030. And as transition is happening, and in most of the cases, the main criteria regarding capacity addition, in spite of, although the planning has been already done, we are seeing that the first approaches are always based on prices. The cost reduction for next plants to be designed and constructed is really key for demonstrate that CSP plants can have a role in the future, and showing that we can just reach prices aligned more or less with the common with the prices which are now in the energy and electricity markets in all the countries, which is in the range of 5 cents of euro per kilowatt hour within this decade. But perhaps some of you already heard this couple of messages from me, which is don't miss the focus. And the focus is that CSP or STE plants are either large or they will not play any role in the future. Only large plants are feasible, and therefore nice concepts, but with the scalability issues, in my opinion, will not likely reach the commercial stage. It doesn't mean that I am against this kind of research. I think it's good to do, but I mean the focus to say, okay, I would like to research on this or this other project should be based on the scalability that this plan can show, or this idea can show, to become really commercial. And the second one is something that sometimes is, or at least until a couple of years ago, was completely, disregarded, which was the possibility that all the concepts, commercial concepts, should show just to be in the market, which is the possibility to separate, to decouple completely the collection of solar energy and the dispatch of electricity. Otherwise, if you have a concept that need to produce electricity when the sun is shining, forget about that, because you are going to produce, although you have storage, the problem is that during a big part of your production, you are going to compete with PV prices, and this is not, there's no way just to compete with them. So those are the two concepts that, in my opinion, for the research community should be taken into account, just to just focus on what can be really commercial and can really help the sector to be deployed. And there are always, like always, two complementary approaches, and both are necessary. There are radical innovations that will, provided that those radical innovations fulfill the two above mentioned criteria, but okay, they should demonstrate first in lab, second in a demo scale, and therefore just to become bankable. And I think there will be in the future, I'm quite sure, that only radical innovations will be the ones that will be, if I'm thinking of the CSP plans in 2040, there will be nothing similar to the plans that we have now. So radical innovations are completely necessary. But the question is that no one of these radical innovations will become bankable in this decade. And as we need to reach the transition goals for 2030 in many countries, I just would like to focus on what I call incremental innovations. And I want to show you that there is a lot of room for cost reduction with already proven components and some systems. So let's explore it. Initial considerations: market volume. Market volume is the driver, the main driver, just to push for these incremental innovations, because as soon as you have a lot of factors and a lot of competition among them, there will be alone or just in cooperation with research institutes, they will try to do as much as possible just to become more competitive than the neighbor. And in this case, market is the main driver for reducing costs without any doubt. But the improvements that should be implemented, I think this is a new curve that I'm using for the first time, which shows which is the impact in the LCOE of the plants, the cost of generation of electricity in the plants. Another thing is the auction price that you can get in the market, and the PPAs that you can just sign depending on different terms and conditions for duration of the contracts and things like that. But LCOE, basic LCOE, there will be the three main variables, which is CAPEX, so investments, OPEX, which is operational cost, and energy, which is the performance, the efficiency of the plant. The relative influence of all these three factors is if you reduce by 25% the cost of CAPEX, the cost of OPEX, or you increase by 25% the energy efficiency of the plant, the energy which is delivered by a plant, these are the impacts that you are going to have in the final LCOE of your production of electricity. So you may see that CAPEX is the most important factor, but also increasing efficiency is really close to it. So I think we have to focus mainly, well, everything counts. We have to focus on all kinds of possibilities for price reduction, but mainly increase of efficiency and CAPEX are the two ones that can just by certain modifications or implementation of improvements can really provide very good prices. Also, enlarging the size of plants is also a way to go, and also confidence on CSP reliability will also reduce financial risks and insurance costs. So that's also two things that has to be taken into account. But just let me focus on incremental modifications that affect either lower CAPEX, lower OPEX, or increase of efficiency of the plants. At system level, there is something that I am already advocating since some time ago, and this was the basis of including the 5 gigawatts in the Spanish plants, is the double future role that CSP plants can play. Until now, we are only used to consider that CSP plant will produce electricity, and we talk about LCOE or PPA for this electricity, and that's all. But we have a lot of possibilities to operate our plants at a large extent in a complementary way, in a complete independent way, as the generation of electricity profile, which has been already requested to our plan. And we can have a lot of additional values for this kind of operation. So just by considering the kind of services that we can sell, for instance, in terms of strategic reserve, in terms of curtailments collections, or in terms of price arbitration, we can just reduce the cost, the price of the electricity, because we are going to have another sources of revenues. We can reduce by 15% the LCOE of our plants if we are telling only about selling electricity. I'm going to talk about this point much more in detail in my second speech that I will deliver in a couple of hours from now in this seminar as well. The second is the choice between parabolic trough or tower plant. I mean, this is something that sometimes has been already, considered, and other times has been already requested. And so I think we have to take into account that the parabolic troughs perform very bad in latitudes above 30 degrees. And sometimes we are seeing that a lot of parabolic trough plants has been built in latitudes like Spain, for instance, 37 or 38 degrees. And this is, in my opinion, is a bad choice. So I think just simply considering the cosine factor of the sun, we can make good decisions, and we can just increase the efficiency and therefore reducing the cost of electricity with a proper choosing of the system concept as itself. And third one is the PV auxiliary installations. Until now, in many cases, putting a PV plant has been forbidden aside a CSP plant. But now, if we consider that we can just provide the internal consumption of the plants at a PV price instead of provide this as a CSP price, we can just, by putting small installations, less than 10% of the total power of the plant, nominal power of the plant, we can just reduce by up to 5% the cost of electricity. So this is something that has to be explored, and it really makes sense to explore it. As a system level, what I recommend to promoters to explore. So multi-tower approach. I'm going to elaborate a little bit more in the next slide, so I just leave it here. But trying to make solar tower plants modular, flexible, and scalable, I think the multi-tower approach with a single power block and with a single storage system may be an option. And I will give you some details and some calculations that I did for supporting this idea. Receivers in the northern field can be also protected much more than receivers in surrounded fields, and we can increase the efficiency just by not by putting a cavity receiver, which is more weighty and more costly, but just by protecting a little bit the receiver, which is not possible in surrounding fields, and this can be done very easily in northern fields, which are associated with the first point, the multi-tower approach, and I will explain you afterwards. And also, wireless heliostats for electricity and communications could also reduce the cost of the infrastructure a lot in those kind of things. For parabolic troughs, I think HTF is the key for reducing costs, I think, as a concept itself. And I think a trade-off between piping diameter and pumping power might significantly reduce the investments as the oil costs a lot. And just by having a lot of big collectors, big headers, big pumping systems apart from the collector themselves, from the absorber tubes, this is something that really makes sense to explore. And just by increasing a little bit the pumping power, you can reduce a lot the capex of the plant. So I think this is something that, in my opinion, should be explored. And this, in some way, explains the difference between the cost of the Nord 2 in Morocco and the Nord 1. So this was one of the main improvements which has been done, and the price has been reduced considerably. And new HTA fluids, more environmental friendly and less costly, will also help in this idea. Storage, new salt mixtures with more delta T, not only above but also below. So low temperatures are also important, just to increase the delta T and the capacity of the storage is something is also important. Also, solutions considering internal insulation in the tanks may be considered just to reduce issues and also just to reduce the cost of the tanks themselves. And power conversion, I'm also advocating since a long time ago that simply downsizing commercial supercritical and steam turbines, we can improve 3 percentage points the efficiency of the plants. And just increasing any increase of efficiency, relative increase of efficiency of any single subsystem will immediately translate to in the same figure regarding the efficiency of the plant or the whole plant. So I think it's very important to consider subsystem by subsystem just for increasing the efficiency of the plant. Talking about multi-towers, this is a paper that I presented in the Solar Paces 2019 in Korea, and shows you that if you split a 150 surrounded field by 5 times 30 megawatts equivalent electricity northern field plants, you can just have an increase in efficiency of 21%. This is something which sounds very important. That's not only reduce the cost of the capex of the half part of the plant, which is the heliostat field, but also increase by 21% the efficiency of the whole plant, not only of the heliostat field, of the whole plant, and that is very important. So it is true that you can just, by doing this approach, you can have modular plants, so you don't have a limit in 150. You can go much higher. You can go 200, you can go 500 even, and you can just even use commercial supercritical steam turbines in those plants consisting of modular heliostat fields and receivers subsystems. It is very important. The reliability of the plants will be increased because you don't have one single receiver. You have 5 or 10 receivers, and so you can just afford just to have one of them in maintenance and just not having the complete plant already stopped. And also thermodynamic conversion efficiency will be much higher. We use, because of the size, already existing supercritical steam turbines. The main drawback is the cost of the long molten salt piping between receivers and central storage systems. So I don't say that you can save 20% in the capex. Perhaps you only save 5% in the capex, but you increase 20% the efficiency of the plant. So you can have a very important impact in the cost of the reducing cost of the kilowatt hour produced. At component level, there is alone. I am only focused on the mirror field because in all subsystems of the plant, similar ideas for cost reduction may also apply. But just for providing you examples, at component level in the mirror field, the heliostat, there is a big discussion whether it's better to go larger or smaller with the heliostats. I don't have well, my personal opinion is that large is better, but I don't have a real supported assessment in this regard. The only fact that I observed is that current manufacturers have different starting points, but all of them, independent on which is the starting points. For instance, Cener is 120 square meters, Bright Source is 7 square meters, but all of them are going larger. So in my opinion, going larger is a right way to proceed. Beam quality and tracking accuracy. This was part of my doctoral thesis long time ago, and I say that when you have a big heliostat field, you may double the error of 3/4 of the heliostats in the fields without having any kind of impact in the efficiency of the plant. Imagine, so you can just use not high quality heliostat. You can use low quality heliostat for a big part of the field, and the energy that you will put into the receiver will be exactly the same, because the size of the receiver is designed to capture the image of the heliostat which are far away from the receiver. But for those which are just at the middle part of the heliostat field, it doesn't matter really to have double the error. They will put all the energy inside the receiver. So this is something that, in my opinion, should be explored. As the same with facets, and they can be simple designs. They can be focused. They using flat facets.
他应该昨天给我试一下，对吧？
Excuse me.
他可能哪国人都没像我这么折腾的。
There is a. Can you mute Professor Wang? Can you mute the microphone, please? And also, well, a stow down. This is something that we did in the past, but now nobody is doing a stow down. But I think in some places, a stowing down will allow for higher reflectivity during the whole life of the plant, and also less cleaning needs, water, and also, manpower, which is also important just to reduce the OPEX cost. Rectangular ratio, 1/4 is better than square. and this has been done square many times, and 1/4 will be much better. And also, alternative shapes to reduce blocking may also allow for more compact and more efficient fields. An advisable trade-off should be interesting in this point. Concretely, there's a pedestal foundation, as the Moroccans did in the North 3, may be a good choice. Linear hydraulic actuators may be preferable to expensive gearboxes. So those are simple examples that can reduce the capex and increase the efficiency of the plants, or really do both at the same time.
Luis,
in parabolic troughs,
we should be concluding. The time
I only have the conclusion slide. Parabolic troughs, again, going larger with the aperture and survey size tubes may reduce also field investment costs, and also finding better solutions for swivel joints and flexible hoses will also reduce the operational maintenance related costs and protection environments issues. And so just for concluding is, so beside the positive impact of larger market volume, and before radical innovations become commercial, some of them will do, some others not, there is enough room for cost reduction of solar thermal electricity applying incremental innovations to the current designs. As you have already seen in my examples that I've already presented to you, and reducing at least 1/3 of the cost of electricity as compared with the cost of the latest awarded project would be really feasible, and we have to be convinced on that, with bankable design improvements, operational maintenance optimized procedures, and smart operational approaches as the use of storage for additional services to the system. And so that's all I want to say to you, and I thank you for your attention. I am open for any kind of questions you may have. Thank you very much.
Thank you very much. Thank you very much, Luis, for your very interesting presentation. I think there have been many ideas that will be worth discussing. Now we'll go to the next one. I don't know what's. We'll go to the second presentation of this panel. The title is Progress in Heat Transfer Research for High Temperature Solar Thermal Applications. And the presenter is Professor Lipinski, leader of the Solar Thermal Energy Group of the Australian National University. Professor Lipinski, the floor is yours.
Thank you very much for the introduction. Thank you very much for the invitation. Can you see and hear me well as the slides?
Yes, yes, we can see the slide, and yes, everything.
So I'm going to give a short overview presentation on challenges in heat transfer research for high temperature solar thermal applications. My talk is going to be half technical, but I did my best to avoid equations, so I will focus on overview of the concepts. This presentation is based on our recent review publications that has been published in Applied Thermal Engineering, plus a number of topics that were captured in previous review literature, as well as the original literature cited in those references. I'm going to show a number of figures, and they have been reproduced from the above references, and the credits have been given in those references as well. So I'm going to talk about heat transfer. Let's start with the source of the thermal energy, which is the sun. We all know it can be modeled as a black body at the effective temperature of 5,780 Kelvin. As the radiation arrives at the Earth's orbit, we have a flux of about 1,367 watts per square meter. And this radiation is further attenuated as a result of propagation through the Earth's atmosphere due to attenuation in various atmospheric gases as well impurities. Now, this is the starting point to modeling and analyzing heat transfer in solar thermal applications. Now, I'm going to focus only on high temperature solar thermal applications, both for production, generation of power, and also for thermochemical applications, production of fuels and other materials. Now, we obtain high fluxes at the aperture of a solar receiver from the diluted or just natural incident solar radiation using solar concentrators. And this can be one-stage solar concentrators or two-stage solar concentrators, which can be parabolic dishes, heliostat fields in different configurations, or linear concentrators. For research, we also use solar furnaces and solar fluxes, which can give us very high concentration ratios and controlled experimental conditions, which are very good, for example, for model validation. Now, we characterize the concentrated radiation at the aperture of a solar receiver using a concentration ratio. There are multiple definitions. In general, there is the power, radiant power at the aperture to the radiant power intercepted by the aperture of the solar collector. Now, once we have this concentrated radiation, we optimize the systems for maximum absorption and other performance characteristics. We deal, in this field, we deal with truly multi-scale problems in space and time. At the larger scales, we can have to analyze transport phenomena. This is mostly radiation in large scales ranging from tens to hundreds of meters. And then at smaller scales, we deal with transport phenomena in receivers or reactors. And then in even smaller scales, we deal with components of those receivers or reactors, which can be participating media, which can be construction materials, reactor walls, cavity walls, and so on. And finally, we have the smallest scales, which are the individual features of the constituents of those components of reactors or receivers. This can be particles, struts, pores, and other elements inside the receivers or reactors. Now, let me first start with the trapping of radiation problem on solar receivers. So there are two basic types of receivers: external receivers and cavity receivers. In the case of external receivers, the trapping is achieved by modifying the surface of such receivers, for example, by adding fins, and then by appropriately shaping the channels and tubes where heat transfer occurs between the absorbed radiation, and the enthalpy change of the flowing fluid. And then we have volumetric receivers as well, or we have cavity receivers, such as the one developed at the Australian National University in a project led by John Pye. Now, often the tubes can have complex shapes, for example, with spirals, as shown here in figure F. Now, at the smallest scale, we can trap light in coatings, and we can use the traditional coatings such as the pyromark with its micro, nano, porous structure, or some pigmented coatings, for example, with titania particles, or multi-layer coatings. These are different approaches, examples of different approaches to enhance absorption and to maximize heat transfer from the absorbing surface into the receiver, into other elements. Now, once we capture this radiation, the next challenge is to minimize re-radiation, and we cannot do much here because of the black body emission or the emission from the surfaces or cavities. And the other potential loss are convection losses. There can be natural convection losses. This is the left part of the figure, or forced and mixed convection losses. This is the right part of the figure. What we see here is the Grashof number. The higher is that number, the stronger are the losses, as a function for the natural convection of the volumetric expansion coefficient, and on the right-hand side, this is for forced mixed convection of the square of the Reynolds number of the flow around the receiver or the cavity receiver. Now, we can see here experimental data in blue. We can see here numerical data in red. So there is a significant volume of work done since the late 80s to the present day. We have summarized all these studies in our review paper, and this plot is a basically single stop for having this information captured in one place. Now, I would like to show two examples of studies on characterizing convective heat losses from solar receivers. The first is this is a project related to convective losses in cavity receivers. In this study, it was identified that there are two zones of interaction for heat transfer between a cavity and the surrounding air. The top is the zone is the stagnation zone, and then the bottom zone is the convection zone where the actual movement occurs. And such systems have been studied and characterized as a function of the tilt angle, as a function of the dimensionless geometrical parameters, fluid properties, wind flows, and so on. Another example of a study is a convective heat transfer around an external receiver. Here it is a billboard receiver, and the study included investigation of the effects of the wind flow around such a receiver as a function of the attack angle and wind velocities. So these are the challenges, because significant challenges, because these losses, convective losses, are responsible basically for lowering the thermal efficiency of receivers. It's the concentrated solar radiation, solar flux is very expensive if we take into account how much it costs to build heliostat fields and set up the plants. And so that we have to ensure we really minimize those convective losses right at the receiver, because these losses directly affect the techno-economics. The next topic I would like to mention, and is in this selected group of challenges in heat transfer, is the heat transfer in liquid metals, in particular in liquid sodium. This work has re-emerged in the solar thermal community in the recent years, and has been motivated also by the developments in Australia. The company Solar has built their demonstration plant where sodium is used as the heat transfer fluid and storage medium. And of course, there is a lot of knowledge developed previously in Spain, in the United States, and in the nuclear reactor community, where sodium is used as the liquid coolant. Now, ANU, the Australian National University, collaborates with Solar and the community, and we have established here a lab for studying heat transfer in liquid and boiling sodium flows. This work is led by Dr. Joe Coventry, who is the principal investigator of that lab. You can see here the schematic CAD drawing of the sodium loop here on the left, and on the right, the actual sodium loop built in the lab and connected here to an energy storage unit. Behind that lab, there is the second enclosure where we have the ANU high flux solar simulator. There is a solar receiver being designed, which will capture the radiation from the solar simulator, hit the sodium, and thus drive the sodium loop. Now, there are significant challenges in that field associated with understanding the heat transfer and modeling heat transfer. Single-phase CFD models have been developed for sodium flows, and more challenges exist in multi-phase flows where we have bubbles and vapor formation and bubble growth. So we have started to study thermophysics of the process of bubble growth in detail here at the ANU. There are also studies elsewhere. And the next challenge is how to incorporate the physics of the growing bubbles into bulk flow of the basically bubbling multi-phase flow of liquid metals. The modelers and experimentalists will have a lot of work to understand the phenomena in such bubbling flows and basically to obtain meaningful results under controlled experimental conditions. The next topic I selected for this short review is the overview of heat transfer challenges in disperse media. There are very many types of dispersed or heterogeneous media found in high temperature solar thermal energy conversion. So we have structures, nanostructures, microstructures, macrostructures. We have particulate media, fluidized beds, packed beds, suspensions of particles in gases and liquids. And understanding heat transfer in such complex media is a challenge for itself. Now, these days, computers are quite powerful, so it's tempting to adopt the approach of materials by design, to not just passively observe what is possible with a given structure, but how can we optimize systems to maximize absorption of radiation in such structures, for example, in directly irradiated receivers or reactors, to rapidly transport energy between the absorption site and the discharge site in receivers or reaction sites in reactors. How can we confine infrared radiation to minimize infrared emission losses from solar devices? And how we can minimize conduction and convection heat losses from such media. Finally, in particular in chemical reactors, we should also address the challenges of minimizing the mass transport resistance and maximizing chemical reaction rates. Now, two specific cases for dispersed media in these applications are particle gas flows and porous structures. Now, particle gas flows have been studied both for solar receiver applications, for solar power generation applications, as well as in solar chemical reactors. Here we can see examples of the free falling particle curtains, a setup built at CSIRO, which is being used for validation of numerical models. A setup with an expanding vortex reactor that has been developed at the University of Adelaide and with very detailed CFD models. A setup that contains aerosol flow with Syria particles in a solar chemical reactor to reduce cerium dioxide for production of solar fuels. And another reactor with calcium manganite particles that form here a granular flow inside the reactor. In all these cases, the numerical analysis, the understanding of the physics is challenging. There are many advantages of using particle gas systems. First of all, the particles interface with the concentrated solar radiation and pass quite effectively the thermal energy to the flowing gas. So they have the function of being heat exchangers. They can be used in directly irradiated receivers and reactors, and they can attain very high temperatures. So here we can have some thermodynamic benefits when working with high temperatures because of higher efficiency potential. Now, when we study the transport phenomena in such systems, we can see in the literature different models that vary from simple one-dimensional to two-dimensional to three-dimensional, models that have only heat, let's say radiation coupled to chemical kinetics in reacting systems, all the way to multimode heat transfer models with chemistry. Typical approaches to model the multi-phase flows are Euler-Eulers models and Euler-Lagrangian systems. None of them is easy to implement and execute even on fast computers.
Now, Lipinski, Sorry, we should be concluding. Okay.
1 minute. And the last group of processes that I have selected here as an example are porous structures. For example, reticulate porous ceramics, which can be used in solar receivers as effective volumetric absorbers, and reticulate porous ceramics in solar reactors, for example, to split water or carbon dioxide in redox cycles. So here you can see examples from Spain and from ETH Zurich. Now, in all these cases, we need to characterize this media for the transport properties, for optics, radiation, convection, conduction, heat transfer. And recently, we have developed a quite sophisticated approach to shorten computational times to model such systems. If we have single or multiple porosity levels, we can apply volume averaging techniques. And this has been done for the first time in the field just recently for two-level porous materials, where we have large pores, and inside the solid fraction of those larger porosity, we have smaller pores. These are materials developed for solar chemical applications. Now, I'm not going here into details. If you would like to learn more about those challenges, I invite you to look at the references I listed in my presentation, or just contact me directly. So I would like to acknowledge the work of the ANU Solar Thermal Group in the field. Here you can see the group in front of our 500 square meter ANU big dish. Thank you very much for your attention.
Thank you, Professor Lipinski. It has been a very interesting presentation with many suggesting topics to explore. Well, the third and last presentation in this panel is titled CO2 Cycles and CSP, and it will be presented by Mr. Wesley Stein, the Chief Research Scientist of the Solar Technologies CSIRO in Australia. Wes, the floor is yours.
Thank you, Manuel, and thank you for the introduction and also for the invitation to speak. Are you seeing my screen at the moment?
Yes, it's there.
Lovely. Yeah, look, I think we've had a wonderful talk on some fundamental aspects from Wojciech, and Lewis talked about increasing and accelerating commercial uptake by incremental changes. And I think that maybe I maybe squeeze in the middle there of trying to talk about the next generation of technology, making use of some fundamental technological changes. Quickly about the CSIRO, the organisation I'm from, has an advanced solar technologies group, and the high temperature solar thermal group make up a very large percentage of their activity, and represents around about 30 people at the moment. Now, ASTRI is an organisation led by the CSIRO. It stands for the Australian Solar Thermal Research Institute. It has about 110 people at the moment, from management down to postdocs and PhDs. People such as Wojciech and an ANU working on various projects within the ASTRI organisation. It's an 11-year, $110 million, that's Australian dollars, program that comes to a conclusion in the next two and a half years. So we're looking to have some big runs on the board to try and expand the program for longer than 2.5 years. I wanted to talk about where we are today with CSP and where the next generation of CSP could be going or coming from. I think Lewis did a fantastic job of talking about those incremental changes that have led to that orange line that you can see there. where typically somewhere between 85 and 90% learning rate is typical of the CSP cost reductions over the last decade or so around the world, and that's been quite critical. But of course, CSP's made some great advances, but so have the other technologies as well. So I really think there's a need for an additional disruptive change to CSP, which is what I've called next generation there. And you can see that there is an incremental change that takes place, and I'll talk about some of the technologies that can do that. But of course, once those new technologies are in place, we still need the incremental changes to continue to happen as well. For example, new heliostats, better heat transfer fluids, storage, etc. So all of these things, incremental and disruptive changes, need to take place together. I'd like to show here the sorts of performance targets and cost targets that we have in place for the system. I won't go through today's position, but the targets that we have for the future are around about $80 per square metre for heliostats. That's fully installed. $150 per kilowatt thermal for the receiver. Providing temperatures to the storage of greater than 720 degrees C. The storage itself needs to have a cost of $20 per kilowatt hour thermal or less. The turbine cycle needs to be 50% efficiency and no more expensive than they are today at around about $1,000 per kilowatt electric. We think that that 20%, or 10 percentage points, but it's 20% relative performance improvement in the turbine is a critical factor in the next generation of CSP, and is the role that supercritical CO2 can play. The important thing about that is that if you improve the efficiency of the cycle, then all of the other components upstream, the heliostats, the receivers, and the storage, are all downsized. They all reduce in capital cost, and what we need to be certain of is that we don't kill the goose at the same time. We don't want to have increased efficiency, but have such high temperatures and material limits and things like that, that the capital cost also increases and leads to no change in LCOE. So we need to be very careful about the way we do these changes. Just looking at where steam turbines are today and some of the characteristics. I'm glad that Lewis did mention the advanced ultra supercritical cycles that are there on the left. That Toshiba probably leads the world today in this space. They're typically very large machines, no less than 400 megawatts and typically up to 1,000 megawatts or more. I think that we've moved beyond just supercritical. We've even moved beyond ultra supercritical now, and we're up to advanced ultra supercritical, which has got 700 degrees inlet temperatures, 35 megapascal inlet pressure, 2 stages of reheat at 720 degrees C. But you're still only talking about 48% efficiency, even with those very high conditions. Another characteristic showing up on the top right graph there for typical subcritical steam turbines is that once the size gets below about 50 megawatts, the dollars per kilowatt starts to increase dramatically. And this has been one of the fundamental things that have driven the way that CSP has moved over the last 2 or 3 decades. And that is that it's been wedded to steam turbines, therefore the projects need to be very big to get the economies of scale of those large steam turbines. I'll show shortly that maybe supercritical CO2 can fill that space in between maybe 10 up to 50 megawatts there that steam turbines can't really do. I'll jump to the next slide. First of all, where is the crossover point between steam turbines and supercritical CO2 turbines as you increase the turbine inlet temperature? Now, this particular study by the DOE.
Okay, I found this on the web for how do you increase the temperature now? Check it out.
Well, that's helpful. This particular study showed temperature crossover around about 450 degrees. I've seen other studies that show the crossover is around about 550 degrees, but certainly beyond 550 degrees, supercritical CO2 does start to show a rapid increase in the difference in turbine cycle efficiency. Here in the top graph shows that that below 50 megawatts, the efficiency performance of the supercritical CO2 shown in the orange curve there is much better. It's still dropping, of course, but it's not dropping as quickly as the blue curve, which is the steam turbine performance. There's also the beneficial impact of higher temperature performance. And in the bottom graph there, I've plotted turbine cycle efficiency versus turbine capacity, but the blue to orange to grey to yellow curves represent increasing turbine inlet temperatures. And you can see that there's quite a marked difference as you increase the turbine inlet temperature with efficiency reaching over 50%. On this graph, I really wanted to show I've chosen a 20 megawatt steam turbine here just to show the complexity that even in a very small steam turbine, they're still quite complex machines and quite large. 14 megawatt supercritical CO2 turbine there is shown in comparison. The one he's holding is obviously plastic, but they're still very small, but they're very simple. It's one of the things that I see as an advantage for supercritical CO2 in the future, that there's probably 3 or 4 big steam turbine manufacturers in the world at the moment, maybe only 3. And so there's not very much competition. But if you can develop a supercritical CO2 turbine market, I could see additive manufacturing opening up many companies in the world who would get into this space and therefore reduce the cost dramatically of these turbine units. Some supercritical CO2 turbine fundamentals. You're operating at above the critical point at all times. In the temperature entropy plot on the left, we're introducing compressor work over on the left-hand side there. We then preheat the supercritical CO2 with recuperated heat from the low temperature recuperator, then the high temperature recuperator. And that all happens before the real heat gets added from, in our case, the solar field or the thermal storage. The turbine work is completed, and the CO2 flows back through the recuperators back to the start again. And there's only a pressure ratio there of around about 2 to 2.5 times because it is a closed cycle. On the right-hand side, I show a relatively small turbine developed by Sandia as a concept 10 years ago. It's only got about 8 megawatts net capacity, but it's got 55% efficiency. And that's primarily due to having 2 stages of reheat, a couple of stages of recompression. But the point I'd like to make here is that even though you might be able to design a really nice turbine, expander and compressor, the recuperators themselves are critical pieces of equipment. And you can see there, if you can read it, that those recuperators are recovering or exchanging around about 34 megawatts thermal of heat in a cycle that's only producing 8 megawatts electric. So those recuperators are huge, and we shouldn't lose sight of the fact that heat exchange is a critical part of supercritical CO2. Some of the properties that make CO2 interesting, particularly around the critical point there. You see that the compressibility rises very quickly once you get above the critical point of 31 degrees Celsius. And that has an impact in CSP, SCO2 cycles, in high ambient temperature conditions. And down on the bottom left, there's a table just showing that there's a range of different fluids that have been considered as working fluids in turbines. Carbon dioxide in its supercritical state has the properties that are most beneficial, but other mixtures have been tried with carbon dioxide, such as SF6, xenon, and some organic compounds. Now, it's not all a bed of roses or of rose petals. There are some thorns in this SCO2 story as well. Number one is that there's limited turbine suppliers in the world. At the moment, if you wanted to try and get a turbine from somewhere, you could probably get one from Ecogen, who've been working for more than 10 years on these turbines. GTI have got their STEP program to build a 10 megawatt 700 degree unit next year. Toshiba and Net Power are building the 50 megawatt thermal alum cycle in Texas. GE have apparently said they would build a turbine for a customer. EDF and Zhejiang in China are replacing a 10 megawatt CSP steam turbine demonstration with a CSP steam turbine demonstration with a supercritical CO2 turbine. And Peregrine have got their 1 megawatt very high pressure technology. So no really commercial entities at the moment, and it'll probably still be a few years away before that's really possible. Then there's the impact of the higher temperatures on the other components in the CSP cycle. If higher temperatures are to be realised, then there's no free lunches, and receivers and storage, and even heliostat precision all require new technology advances so that higher turbine efficiency can be realised. We look here at the impact of SCO2 turbine costs on tests. In this table, there's a 560 degree turbine inlet temperature, 46% efficiency, just over $1,000 per kilowatt for the power block, and we indicate the sorts of thermal energy storage costs that would be needed to keep the electricity price at less than 9 cents. At 700 degrees Celsius, the efficiency goes up to over 50%, but because we're now using a more exotic steel, the capital cost of the block has gone up as well, and in this particular study, they estimated nearly $1,600 per kilowatt. And so the level of thermal energy storage costs that you need to provide to still reach 9 cents per kilowatt hour is a lot less. So these things all need to be considered and modelled as a complete integrated system. Ambient temperature I mentioned before. This plot shows that if you designed a system for 45 degrees Celsius, then your cooler would have a very large surface area. And it would mean that for the majority of the year, 99% of the year, the cooler is working very, very effectively because it's effectively oversized. If, however, you only designed your cooler for a 33 degrees Celsius compressor inlet design temperature, then for a lot of the year, especially in places like Daggett in California, the ambient temperature is a lot higher, therefore the compressor inlet temperature is a lot higher, and you're getting into that compressibility range of the supercritical CO2 that reduces performance. And you can see there that there's nearly in Daggett, a 6% difference between designing for a 45 degree day and a 33 degree day. So that's a critical point as well. And just 2 slides to finish off. First of all,
we are running out of time.
Okay.
Take into account, please.
Thanks, Manuel. I'll finish off very quickly. First of all, the need for higher temperature impacts on the heat transfer fluid, and we move to sodium, as Wojciech mentioned before, because it can go to over 700 degrees, and it has very high thermal conductivity, and it's relatively mature. Or alternatively, particle technology. And there's a lot of work going on in Australia and in the US at the moment, and in DLR in Germany as well, to develop technologies that use particles, which are very cheap. They can go to very high temperatures, but there are some issues, such as the development of key subsystems, bulk material handling, erosion, loss of particles through the receiver, and limited operation experience to date. So that's where I finished. I just wanted to let you know that it's not all beer and skittles, and that there are some problems to be overcome if supercritical CO2 is to be realised. Thanks for your time.
Thank you very much, Wes. It has been a very interesting presentation, especially this possibility of using supercritical CO2 turbines in more or less near future and improve the efficiency. It's worth taking into account. I'm afraid we have run out of time for discussion. I don't know if we can still take one or two questions, or if I have no. I don't see any questions at the moment from the audience. I think there have been many topics worth discussing, but or perhaps I'll just pose one question if there's no other from the audience. It's from the beginning of the session. Luis, you mentioned that only large plants make sense in the field of CSP. Is this consideration only limited to the CSP field, or do you think that smaller plants could make sense for industrial heat?
Yes. Can you hear me, Manuel?
Yes.
Yeah? Yes. Okay. Yeah. Right. So, well, I have perhaps to fine-tune my assessment or my statement. Well, what I want to say is that for large electricity deployment of plants, I think that only large plants are possible to be considered in the planning systems of different countries because of the price. But it is true that large plants will produce electricity at much lower cost than smaller plants. But there might be places, I am thinking, for instance, on the Canary Islands, perhaps in Cyprus, where CSP can play a very important role because thermal storage can be a kind of buffer for the introduction of a lot of non-dispatchable technologies like wind and PV. And I think in those places, some 50 megawatt power plant or even 25 megawatt power plant with thermal storage can make sense. But those markets will be kind of niche markets, and I don't think that the deployment of CSP can be based, and the reduction in cost of CSP can be based of those very small markets. For sure, for industrial heat applications, I think is the contrary. I think you have to be very close to the user, and in this case, only small plants and distributed heat production plants make sense. I think is not conducting heat long distances. I think this is a nonsense. Conducting electricity, this is already proven, and this is the way that we are living. But for industrial heat, I think small plants may be based on Fresnel with fixed absorber tubes, or maybe also based in parabolic troughs. Might find a way and might find a place in the market for sure.
Okay. Thank you very much. I think we have to finish the session. I wish to thank all of you very much for your participation and your very interesting presentations, and all the attendees. And well, I hope that we will have the opportunity to talk about this, not only in this forum, but in other forums. Thank you very much. And,
thank you, Manuel. Thank you. Bye-bye.
Bye.
Thank you very much to all of you, and thank you for an excellent session. We will start in 5 minutes the next session. Until then, oh. So,
okay. Bye.
Okay.
Good. Good afternoon to everybody online and in the various channels. We are dispatching this event, and thank you to all for being there and for the organizer for taking this the initiative of this conference. My name is Marcel Bia. I'm heading the business association, the Estella, which is a European association defending the interest of the CSP sector. And we are now in the second session of the day, labeled International Programs to Accelerate the Market Deployment of CSP Technologies. Every word matters, but I will come back to this one. The three speakers in these sessions are first Piero De Bonis, who will talk about the European programs. Then Avi Schultz for the US. Hi, Avi. I see you not finally. I didn't know whether you were. And at the end, Professor Wang, Sifeng Wang from the Chinese Academy of Science. I will not go into the bios of this gentleman, distinguished gentlemen, since they are all online. And as maybe a very short introduction prior to give the floor to the first speaker, to Piero, let me maybe allow me a few remarks. I personally appreciate in reality the coherence of this today's program, in the sense that we have heard already, I don't know whether you guys had the opportunity to listen to the previous session, but we will in reality go a little bit more in alongside what we heard earlier today, seen from the three perspectives on the three continents. So this is the first point. Talking about the title, the point is what in those programs is assessed or supposed to best help the market. The market is an important word in the title of the conference. And I cannot refrain from reminding that R&D is just one element that helps the market, but there is, of course, a massive also impact of how R&D is deployed in the context of political and regulatory specifics of the various countries or continent. The second point, but we will have to listen first what our speakers have to say, and maybe in the discussion following our speakers, we can try to identify whether there is a kind of consistency between those various approaches in those three continents regarding the type of innovation, the type of research, and the type of initiative that is supposed to support the market, as it says, the market or accelerate the market deployment. Without further ado, and being always happy to have Piero in the session, I give you, Piero, the floor for the first presentation. Please.
Thanks, Marcel. Good afternoon. Hello to everybody. I will give a quick overview of activities in terms of programs of the European Union. This presentation is almost similar to the presentation I gave a couple of weeks ago for our implementation working group on concentrated solar power of the Strategic Energy Technology Plan. The Strategic Energy Technology Plan, which was endorsed in September 2017, and the plan sets a number of research and innovation activities, 12, and 2 key targets for CSP in Europe. What has happened since September 2017? In November 2018, in the European Union, we had this communication, which is called the Clean Planet for All, which is the first document in the European Union which set the target of achieving net zero greenhouse gas emissions by 2050. In this communication, concentrated solar power is mentioned as another solar energy source in which the EU is a global technology leader. And the communication, as you can see on the slide, acknowledges also the dispatchability of CSP. And the communication also refers to this document prepared by Solar Basis, Greenpeace, and Estella, the Global Outlook 2016, and where it is mentioned that CSP can reach an installed capacity between 5 and 35 gigawatt by 2030. In December 2018, so almost 1 month later, we finally revised the Renewable Energy Directive. The Renewable Energy Directive was first approved in 2009. So almost 10 years later, we have a revision of this important piece of the European Union legislation. And in this revision, there is this target set for 2030 of at least 32% of renewable energy in the gross final consumption in the European Union. An important aspect is that the December 2018 revision again reconfirms the cooperation mechanisms, which are mechanisms which allow 2 or more member states to collaborate on joint projects for the development of renewable energy projects. 1 year later, at the end of 2019, we have the National Energy and Climate Plans. These are a requirement from the regulation, which is the regulation on the governance of the Energy Union. And these plans, as the name says, in their plans, each member state has to set ambitions and objectives in terms of energy and climate activities from 2021 to 2030. These plans were first submitted, then reviewed by the European Commission. The final version is now available at the link you can see on this slide. And in a way, as I said, these plans in a way set the ambition of the member states until 2030, especially in view of achieving a share of 32% of renewable energy in the energy system. Of course, in a way, in the meantime, things have already moved on, because again, in December, at the end of 2019, on the 15th of December 2019, we have the launch of the European Green Deal, which is, I would say, one of the key initiatives of the new European Commission. The new European Commission, I mean, the Commission that took office in December 2019, and the President is Ursula von der Leyen. The European Green Deal is structured along along 8 streams, and you can see that, of course, one of the 8 streams is indeed clean, affordable, and secure energy. The European Green Deal is an overarching policy, and a number of more specific policies have been defined in the meantime. One of which is the European Climate Law. So this is a proposal to enshrine in EU legislation the objective to make the European Union carbon neutral by climate neutral, by 2050. Another important piece of legislation, this came just before the summer this year, is a strategy for energy system integration, which acknowledges more and more the idea that all different components of the energy system, all different also technologies, have to work in a coherent fashion. Then we had also, before the summer, the hydrogen strategy. I think everybody knows that there is a lot of talking now about hydrogen, about the potential of hydrogen. Of course, the key aspect we want for hydrogen is that hydrogen is a source from renewable energy sources. And then we had this 2030 climate target plan package. This is again this package sets in motion a new round of revisions of pieces of EU legislations, because the idea is to increase the ambition in terms of reduction of greenhouse gas emissions. The current target is a 40% reduction by 2030, 30, but now with this piece of legislation, the idea is to go down to 55% in terms of reduction of greenhouse gas emissions. And actually, we had the European Council summit last week, and the objective of achieving the more ambitious objective of 55% was actually approved. So this is the direction we will follow. And to achieve, of course, a higher reduction of greenhouse gas emissions, also we need again to revise some pieces of the legislation. So again, the Renewable Energy Directive will be revised, and as is typical for our pieces of the legislation, there is also an open consultation, and it's possible to participate to this consultation until the 9th of February, and this is the link where you can find the consultation. For initiatives which are very relevant now, of course, we all know we are unfortunately in this pandemic, and the European Union launched Next Generation EU as an instrument for recovery, and it is clearly said that 37% of the activities funded by Next Generation EU have to be spent directly on objectives of the European Green Deal. The Next Generation EU will be implemented by means of a recovery and resilience facility, and each member state will have to develop a national recovery and resilience plan. Plans are being developed at the moment. Of course, there is potential there to launch new renewable energy projects. CSP might be in the picture of those plans. This is our hope indeed. And another important instrument I would like to mention is the so-called taxonomy. So this is a classification which is very the EU level to acknowledge green investments. Also here there is a public consultation which is open for 2 days more, and I can reassure that the electricity generation using considered solar power is anyway considered already as contributed to climate change mitigation. So this is an important result for CSP. The role of CSP is clearly acknowledged in the taxonomy. And I would like to close my presentation by mentioning 3 projects which we have funded in the past 2 years now, with the last calls of Horizon 2020. Horizon 2020 was our framework program for research and innovation from 2014 to 2020. Now we are about to launch Horizon Europe, which will start in 2021. And I would like to mention these 3 projects, which stem from calls which are directly related to consolidated solar power. In 2018, we funded Scarabeus, which has to do with supercritical CO2. Last year, we funded iFlex, which has to do with thermal energy storage in CSP plants. And the last to start is solar SCO2 all, which is again concerned with supercritical CO2. This is the end of my presentation. As you see, in terms of legislation, of course, a lot of activities on the side of the European Union in terms of promoting renewable energy technologies and renewable energy sources, and also on the research side, of course, always a focus on CSP, acknowledging its role, acknowledging its dispatchability. Of course, we have to bear in mind anyway that other technology, which I will say now mainstream renewable energy technologies like wind energy and PV, are of course more and more in the focus. They are reaching incredible targets in terms of install capacity. So, of course, the gap between CSP and those technologies is there. Maybe the gap is even becoming larger. And I think in the CSP community, we have to bear in mind that and see how CSP can play a clear role in this evolving energy system. Thank you.
I'm sorry. I was saying thank you for your time management. This was perfect. And as a wrap up, if the takeaway of what you said is that the action of the Union, of the European Union, is essentially, of course, focusing on the legislative. This is the job of the Commission, the legislative framework. And without a direct, let's say, even if it's included, as CSP is included, but there is no direct, let's say, legislation provided by the Union regarding CSP. However, what we heard by Pierre is that a direct support to CSP is provided via, on the research side, via the funding to a number, could be higher, but this is still a number of CSP projects and we will maybe talk later if we have time, to which extent those projects are consistent with the ideas we heard in the previous section. Now, I give the mic to Avi, who will talk about the US. A lot of US in the news, please, you have now the floor, Avi. Thanks.
Great, thank you very much for the introduction, Marcel, and thank you to Manuel and the organizers for the invitation. I'm very happy to be here, and good morning to everyone, or at least morning from Washington, D.C., where I am. Thank you for having me. I'm going to give a little bit of a quick overview of course, our research program that we've been supporting here at DOE on CSP with a couple of recent announcements to give you some idea of where we're heading. Of course, as many of you know, our focus in the DOE program has really been focused on the affordability of CSP, with a research program geared towards lowering the levelized cost of electricity for CSP to make it cost competitive with conventional electricity sources. When we really started this effort in earnest in 2010, as you all likely know, the CSP was far more expensive than it is today. We baselined that at about 21 cents per kilowatt hour. We currently baseline CSP, if it were to be built in the US, given US kind of typical costs and expectations, that it would be about 10 cents per kilowatt hour today. We're aiming for about another 50% decrease in the cost of CSP by 2030. And if we're able to achieve that cost decrease, the plot on the right side of my screen here shows analysis that the National Renewable Energy Laboratory performed last year that indicates that if we hit that 5 cent target, that will in fact lead to fairly cost competitive deployment of CSP in the realm of hundreds of gigawatts of CSP in the US. Of course, that's subject to many sensitivities based on your assumptions of what else is happening in the US energy sector. Based on that 5 cent target, we've developed a number of specific component cost and performance targets that we've been trying to achieve through competitive solicitations for research and development. I think that many of you are likely familiar with that lately we've been putting out and on a schedule of approximately one a year with a variation of focuses on either very specific issues in terms of gaps that we see in research or broad solicitations for general research in CSP. And I'll talk a little bit about our most recent announcement from our 2020 funding opportunity. Out of all of those solicitations, we currently have an active research portfolio in DOE of about $185 million worth of projects on CSP research, split up, as you see here in that pie graph, through various kinds of institutions, including university researchers, the US national laboratories, as well as for-profit industrial companies, both large and small, as well as nonprofit research institutes. I encourage you, if you're interested, I'm only going to be able to, of course, scratch the surface of all of these projects. If you're really interested in learning more about everything we're working on, please visit our website that has at least short descriptions of all the projects in our full research portfolio. I'll also just say that those more than 100 active projects that we currently have right now vary significantly from very small seedling projects that we've funded in order to kind of explore interesting novel concepts, to large demonstration level multi-million-dollar projects. And I'll talk a little bit about a couple of those big initiatives that we've been working on that we think are really exciting to push forward the maturity of a number of interesting concepts in the CSP space. Another way of showing that figure that I showed kind of with the diagram of the CSP plant is this roadmap that we've mapped out that is just one potential pathway. It's not the only pathway, but it's one potential pathway we've looked at to get to that 5 cent per kilowatt hour for a baseload type CSP plant. And what I'm going to start out with in diving a little bit more into the research is to draw your attention to the fact that the power block and the power cycle is one of the most important sensitivities that we think there is in terms of lowering the LCOE. And that's both the capital cost of the power block as well as the efficiency of the power cycle. And we're targeting, by looking at advanced power cycles, and as you all likely know, specifically at supercritical carbon dioxide power cycles, at hitting a power cycle cost of about $900 per kilowatt electric, and a efficiency of 50% thermal to electric. And as I just kind of course, gave the game away, we're really focused on these supercritical carbon dioxide Brayton cycles for a number of reasons. Chief among them really is the efficiency that is modeled to be able to be achievable 50% at about a 720 degrees Celsius turbine inlet temperature, as well as due to the density of supercritical carbon dioxide as a working fluid, the compactness and therefore the smaller footprint that you're able to achieve. And I think you heard a lot already about the advantages of these cycles from Wes Stein earlier today. One other thing that I'll just emphasize that I'm sure Wes did as well, which is the scalability of supercritical carbon dioxide cycles, which we think is really interesting. Of course, one of the challenges for CSP is the limitation in plant size, being essentially really forced to go to about 100 megawatt or larger to be able to maximize the efficiency of conventional steam turbo machinery. We believe that SCO2 cycles should hopefully provide a pathway to open up smaller, more modular CSP plant designs. I'll also, of course, just say that we're working closely on SCO2 technology with other offices in DOE, specifically the fossil energy and nuclear energy offices that, of course, are interested in SCO2 turbines for coupling with other thermal energy sources as well. There is, of course, quite a bit of research to be done on SCO2 cycles. A number of those research efforts that we've been working on are outlined here on this slide. I won't spend too much time going into these in detail, but just to say that what we've really started focusing on is a lot of efforts to improve the manufacturing and materials of construction that are used to really develop pathways for getting the potential cost of these cycles down even lower than folks are thinking these days. And of course, the big announcement that I'd really like to spend a little bit of time on is in our 2020 funding opportunity. As many of you know, we had a topic to solicit a demonstration of a near-term supercritical carbon dioxide cycle powered by thermal energy storage to be able to get to essentially kickstart the commercial development of CSP with thermal energy storage. Of course, as many of you know, we've been working, and I'll talk a little bit about it later on, we've been working on the Gen 3 program, Gen 3 CSP program, which is developing thermal transport systems to deliver high temperature energy to that 720 degrees C supercritical carbon dioxide cycle. But our goal with testbed is to gain experience with SCO2 cycles at temperatures that are really achievable with materials and thermal media that are available today. And so you see here on this slide the project that we selected from that solicitation, which is a project led by Heliogen, which is a startup company based in California, whose core technology is really the heliostat field that they've been developing that has the potential of being much more, much lower capital cost and much more autonomous and therefore easier to operate than conventional heliostat technology. They've teamed with, as you see, a pretty large multi-organizational team, including GE Research, Barbara Nichols, Siemens Gamesa, Parsons as an EPC engineering partner, as well as Sandia and Southwest Research Institute, to put together a proposal for a full integrated demonstration of an SCO2 power block, not just heated by thermal energy storage, but heated by a CSP field to actually provide solar heat to this system at a 5 megawatt scale. And what we really are aiming for with this effort is to be able to stand up and demonstrate this pilot plant, essentially, to be able to provide public operational experience for the SCO2 Brayton cycle to really de-risk the technology for utilities, plant operators, and CSP developers. This is a large effort, as you can see here, with $39 million of DOE funding going to support this, and cost shared by Heliogen and their investors, but with $31 million of their own funds. So this project is currently in negotiation, so I don't unfortunately have more to be able to share on the details of exactly what the plan of this effort is. I hope to, of course, have more details soon as we finalize the contract for this and kick off the project. For the higher temperature system, to be able to get to the efficiency, the 50% thermal to electric efficiencies that I talked about, as I think many of you in the audience are probably familiar with, and I already mentioned, we launched the Gen 3 CSP effort a few years ago to really design the full thermal transport system at a high temperature that's above conventional nitrate salt temperatures to be able to get to those temperatures. And the structure of this program is that we've had 3 competing teams looking at 3 different heat transfer media and thermal transport systems. Sandia leading a solid particle-based pathway, NREL leading essentially a liquid advanced molten chloride salt particularly based system, and Brayton Energy leading what we call the gas system, and as I'll note in a second, what they've really been focusing on is using a supercritical carbon dioxide loop in the receiver of the CSP plant. I'm excited to say we're getting really close to making a decision on which one of those pathways is going to get down selected to what we call phase 3, which is where we're going to award $25 million to one of these pathways to actually build a megawatt scale test facility to demonstrate this thermal system. And phase 2, where they're going to be submitting those designs to DOE, is scheduled to end in January of next year. So in just a few weeks, really, we expect to receive those applications. And then we hope within a short period of time, probably a couple months after that, announce publicly which one of those pathways is going to be selected for phase 3. In the interest of time, I won't dive too much into the specifics of what each of those teams is working on, just to say that over the last 2 years, these teams have done quite a bit of effort to really do detailed engineering designs of their systems. For example, NREL has been working on integrating all different components that they're working on, and really been focused, particularly among other things, on a hot 750 degrees C molten chloride tank design with that's internally insulated, as you can maybe see here on that diagram. Sandia in their particle system has been working really hard and have been able to get some on-sun high temperature tests of their novel falling particle receiver, as well as a particle to SCO2 heat exchanger that they've been able to prototype and pilot and gain a lot of really interesting experience with to inform their test facility design. And Brayton as well has been able to do a lot of work doing detailed testing and prototyping of their receivers, as well as their heat exchanger design for their indirect system, where they're planning to use, as I mentioned, supercritical carbon dioxide in their receiver, and then actually couple that with their own particle thermal energy storage system.
Maybe can you conclude?
So, yes, I'm sorry, I apologize. I'll be very quick. I just want to say that looking towards the future, as we think about the market opportunities for CSP, one focus that we've really been thinking about is how do we increase the flexibility of CSP plants? And really part of that is two different strategies that you see here on this slide. One, thinking about hybrid thermal energy systems where you have indirect thermal energy storage, potentially thermochemical energy storage, where you can generate fuels for long duration storage, or making CSP with thermal energy storage look more like PV with batteries that can serve a bidirectional electricity storage system. And those are concepts that we've been exploring through some recent awards, for example, with Arizona State University coupling to a hydrogen, solar thermal hydrogen production system, or Michigan State University that we just recently started to develop a solid oxide thermochemical storage. I'll skip all these slides in the interest of time and just leave this link up on the slide to mention that if you're interested in what we've been thinking about in terms of future research opportunities, we just recently held a series of virtual workshops. Those slides and workshop summaries can be found on our website at the link here on this slide. So apologies for going a little bit long, but thank you all for your attention. And I'm happy to take some questions if there's time. Thank you.
Thank you, Avi. I think we will take the questions. I have already one from the audience for the European side, but I propose to hear now Professor Wang from China, and then we can try to have a short discussion afterwards, trying to combine questions. Professor Wang, the floor is yours.
Okay. Good morning, good afternoon, and good night, everybody. I'm Zhifeng Wang from Institute of Electricity Engineering, Chinese Academy of Sciences. Today I have two presentations. One is China program. Second is after 1 hour, I have another presentation about China pathway on CSP. Maybe second one more commercial, just more R&D. During this 5 years, from 2019 to 2025, we have funded some projects about related CSP. There are 3 projects already funded. One is a 200 kilowatt supercritical CO2 CSP system. This system will be installed in Yanqing, Badaling, and Beijing. I'm the head of the projects. Second project is a linear metamaterial reflector concentrator. This project just funded in this month, December this year. Third is a very interesting project. Project is a bionic heat transfer technology for PCM heat exchanger. In this presentation, I only introduce the first one, a 200 kilowatt supercritical CO2 CSP system. There include 5 parts. One is the receiver. We use a particle receiver. The receiver didn't like Sundia laboratory, and we use a quarter glass tube inside the particle. This receiver will be installed in Yanqing in next year, April. Second is heat exchanger for the particle and supercritical CO2. Third key equipment is a 200 kilowatt turbine. First is 800 particle tank. Valve and hoist is very important. In the first, we don't know the transportation for the particle is very hard. We just only forecasting some main equipment, for example, receiver, heat exchanger, and turbine. When we install the system after design, we know the tank is very important. Hoist is important. Valve is also important. 5 is a system simulation. It's included in of course, it's integrated the system. It's our tower in Yanqing. I think a lot of people already visited there in 2014 IEA Solar Pieces Conference. holding in Beijing. Then some people visited this plant already in 2014 during the conference. We will install the particle receiver on the inside this cavity. The higher of this cavity is 19.6 from ground, 96 meters from ground. We will install the tank in this position at 76 meters to ground. Then there are two tanks in here and can change the cold particle inside to input the receiver and the hot particle output the receiver to the tank, or it can make a cycle only for the receiver. Then we install a heat exchanger on the ground in this part. If we see now our situation, we have installed some steel frame on the tower. This frame for the receiver is like this. Here is a glass tube. Inside is the particle. The diameter about 0.2 millimeter. And 200 nanometers about 0.2 millimeter. Here is a small tank. The cold particle from here to fall down into this receiver, then be heated. When it fall down, be heated by the solar radiation, concentrated solar radiation. The radiation flux about 500 kilowatt per square meter. You can see this map. Then it can increase about 200 degree from here to here, into 200 degrees, and to here about 800. This means inlet temperature is about 600 or 560. Outer temperature is 800. Then to go down, slide down to the cold tank in this position. We have some tests you can see this map. If the particle diameter large, the efficiency will decrease. For example, if we use a 4 millimeter diameter, the particle is efficiency can up to about 65, but if we use a large one, it decrease to 45, 10 millimeter. So it's the efficiency very related with the particle diameter. Of course, it's related with the flux density. Okay. Second key point is heat exchanger particle and supercritical CO2. Here is our exchanger. Inside is supercritical CO2. Outside is a particle. Particle is fluided bed. We use hot gas, the inlet, to inhale the gas in here. Then to make the particle inside the particle from receiver. Temperature is 800 centigrade. The hot air to make the particle fluided. Then inside the tube is supercritical CO2. And the heat, the hot air can make a cycle in here. This part is a hot air. That hot air is for the particle fluided inside the heat exchanger. That's a system. It's a testing system, not our system in tower. This is a system is where we were installing in the bottom of the tower in next April, next year April. Third part is key part is 200 kilowatt supercritical CO2 turbine system. The turbine system includes the PCHE and turbine and compressor. We design all part of this element. Then we were integrated this all element in next October, about October. maybe in next year, end of next year in December, we can install this system integrated, move to Yanqing. We will install the turbine in this part here, bottom of the tower. Okay, thank you for your attention.
Thank you.
Because I have a presentation, I will explain another issue in next presentation.
All right, thank you very much. Thank you very much for this first presentation. And
yes.
Now we have something like 10 minutes for some question. I mentioned I had a question from the audience popping in. This goes to Piero, rather, because it's about Europe. The question was, now that the European Investment Bank is in the EU's climate bank, can we expect that the bank, will scale up its support to CSPs specifically? It's a very difficult question, probably, to answer. But could you hear me, Piero?
Yes, I heard you. With the bank, maybe some of the audience are not aware. With the bank, the European Commission and the European Investment Bank have already managed for, I would say, 4 or 5 years now, an instrument which is called Innofin EDP, where EDP stands for Energy Demonstration Projects. And it's an instrument where European Union money is used as guarantee for risky projects that have to achieve the first, I would say, pre-commercial plant. This instrument has funded so far, if I recall well, 9 projects. Unfortunately, none so far, I would say, on a complete CSP system. I think we have 1 project on a thermal energy storage system, if I recall well. I'm just using this as an example of the fact that the European Investment Bank, in effect, is actually aware of, is very well aware of renewable energy technology, but it is definitely also aware of the CSP technology.
Right. So I think the question was answered by that, but the guy who put the question has left. So I think we are happy. Now, trying to wrap up and to come to a kind of more general discussion, because it's really difficult to go into the details now of each program. But what we heard so far from these 3 programs, as it say, it was part related to R&D, and we had the very interesting examples of some R&D programs. And more on the European side, we have a kind of a glimpse onto several programs that are more of legal nature, let's call it regulatory, knowing that the European Union is overseeing the energy policies of the member states, but of course it doesn't take the investment decision, but it may guide them. Now, I want to come down to an idea that was tabled by Luis. If we look, or if we remind what we heard so far, to which extent do you believe, fellow speakers, that there is a kind of the story between disruptive research program versus programs or research efforts trying to achieve close to market, maybe closer to market, incremental gains, efficiency gains, or so? What do you see here? A kind of balance, something? It's both sides. Avi, I think you have an opinion on that.
Yeah, I think it's an interesting question. It's one we certainly think about a lot in our DOE program. I mean, I think the simple answer to that question is that I think it's all required. I think it's really important, and I think to a large degree, all 3 of our programs have intentionally tried to design a pipeline of projects. What sometimes we struggle with in that regard is while it's important to create a pipeline, of projects at a lot of different technology maturity levels. Unfortunately, the ones at the highest maturity, and especially by the nature of CSP as large thermal systems, tend to strain the limits of our budgets as government organizations. So what we see is that one of the challenges, that I think we have as primarily research organizations is working to get a kind of community consensus and a political consensus, frankly, on what those demonstration level activities, should be to use our scarce research dollars.
Mm-hmm. Yeah, thank you. And even if we look at research or the examples, and many speakers have not really too much time to go into the details, but if you look at those research, you have the type of supercritical stuff, so really high flying on a very ambitious programs that will be backable maybe only in a few years, and simpler stories, maybe this research on scalability or the demonstration of scalability of new incremental improvements. This is one story, and it addresses the use of CSP on the for the electricity market. But I think it was also you, but also Piero and Professor Wang, implicitly at least, opened the issue on CSP. Next generation of CSP will have to serve both the electricity market, maybe at the we are not there yet, but also to open up research on what Luis again called the decoupling between electricity or the capture of energy, solar energy, and the production of electricity. So this and some missing link. What I don't, what didn't hear so far today or too much is what kind of research do you see going on? I think it was you, Avi, mentioning the hybrid projects, and I recently had a talk, for example, just to give you a bit infeed of my own experience with some guys that were focusing on smart integration, power and gas, and the guy in the industry told me, well, there is a lot of research to do on how this can decently work under sustainable regulatory rules. So how is this story now? My question now is about to you, or any of you, is do you think there is a kind of, or will there be a balance now in the programs between support to CSP technology and maybe what could be named CST technology as a use or the hybridization of some part of the CSP value chain with other technologies to serve short-term needs or ambitions of the different countries? Whoever wants to take the question. Is this something going in? Yeah, Piero?
Yeah, I would say that on our side, in the EU research programs, for sure we will, in a way, slightly move the focus from simple CSP to, as you were saying, CST. So, consolidated solar thermal technologies, and of course, in line with this, in line with the spirit of sector integration, putting consolidated solar thermal technologies to be used where they really bring an added value. This can be a local industrial system. It can be a piece of the vast energy system of a country. It can be a specific regional situation. I think really we are slowly moving away from the simple idea of okay, utility scale consolidated solar power plant located somewhere. So I think this, I will say, is the first reflection, and the second is more an invitation to the possible research performance to look really for opportunities for concentrated solar thermal technologies, to look for opportunities in our EU calls, not only under specific topics, as we call label as CSP with the word CSP in the title, but really to look across several different topics, because I think more and more our topics give the opportunity to use consolidated solar thermal technologies under very different fashions.
Okay, I'm a lucky chairman because questions are popping in. So, and I want to channel this question to you. The one is one participant say it seems that only the U.S. is paying attention to the need of materials for higher temperatures. Is that so? And then I'm looking also at Mr. Wang. High temperature, is this materials and for high temperature use? Is this subject of research also in China?
Yes.
Yes. Good.
Yeah, we use we try several kind of ceramic. Yeah.
Yeah. Okay. So this is maybe the impression that this was only ongoing and in the U.S. is maybe not that.
Tony, I wanted to reply your last question about CST and the CSP. I think is a very interesting topic. Very interesting. We in China we talk often because Chinese PV is very cheap, as you know. Where the CSP go to? I think bi-direction grid is a very good idea. Just Avi mentioned, we have some storage. It's possible for bi-direction, both side direction, to charge and to charge the heat from grid, electricity grid, and we can output the thermal to power and to grid.
Right. Okay. Avi, you want to add something to that about what's going on materials, maybe a little bit more in detail?
Yeah, no, we have done quite a bit of work on materials, and I was really only able to I mean, barely even scratch the surface of that in my presentation. Obviously, with our drive within the Gen 3 program to look at a 720 degree C turbine inlet temperature, that implies something like a 750 degree C thermal energy storage system, and potentially even up to 800 degrees C at the skin of the receiver for a tubular receiver. So there are quite a bit of materials challenges. A lot of our efforts have focused on qualifying new alloys or recently developed alloys, specifically nickel superalloy type materials, and understanding how to use them in industrial settings, right? So really working with a lot of the developers of those alloys to understand, make sure we have the right welding procedures, casting procedures, other kinds of fabrication procedures widely understood, so that that's not a limitation to the commercial deployment of these systems. We're also certainly, Zhifeng talked about ceramics. We're certainly very interested in ceramics as well, and have been looking at a number of novel ceramic or composite materials that we can apply to these systems. I'll say, just very quickly, to not take up too much more time, that a real emphasis in general on in this material efforts for us has been in the primary heat exchanger, where you're trying to transfer heat to, of course, supercritical carbon dioxide as a very high pressure, high temperature fluid, while also, of course, maintaining thin walls. That's really been a challenge, and where we've really seen the biggest opportunity for new materials discovery or development, as well as new manufacturing techniques to develop, compact heat exchanger designs in those contexts. So that definitely has been a focus of our program.
Thank you, Avi. If I'm not mistaken, my watch tells me that we are at the end of our time slot. And I would like at this moment to thank you really sincerely for participating in this. There is much more to comment probably on that, but thank you very much, and have a nice continuation of this following this conference. Bye.
Thank you, Marcelo.
Thank you very much.
Bye. Bye.
Bye.
Bye.
Thank you, Manuel.
Yeah, fellow, are we?
afternoon, everyone. Welcome to the third session of this day with a broad title of Market-Driven Pathways to Deployment of CSP Technologies. So the discussion goes on and the presentations, the deep presentations on CSP technologies go on. I am Theodoros Zachariadis. I'm an Associate Professor of Energy Policy at the Cyprus Institute, and I will be chairing this session, and I hope that you will not need me to remind you that you have about 12 minutes to make your presentations so that we have time for nice discussions as we had also in the previous session. So the first presentation is by Mr. Javier Lara from Pacific Green Technologies. Mr. Lara has a very long CV and great qualifications, but I will not take your time about this. He's the Senior Vice President for CSP at the US-based Pacific Green Technologies Group and the CEO at the international consultancy company Aelius. And he works for the Asian Development Bank and has very long experience with CSP around the world. The title of his presentation is Spain's World-Leading Push for CSP. So, Mr. Lara, the floor and the screen is yours. Great.
Okay, thank you very much for your very nice introduction, and thank you very much to the Cyprus Institute and to the organizers to be so kind to invite me to this event. I am very proud of that. Okay, today my presentation is focused in what will happen in Spain in the next coming years, or what all of us are expecting that will happen in Spain due to the PNIEC, the National Energy and Climate Plan, that, as most of you know, it announced an addition of 5 gigawatts of CSP by 2030. First of all, I will do a quick introduction of my company, and then I will go to the topic of this presentation. Pacific Green Technologies is an American company that have offices not only in the US, but also in Canada, UK, China, Hong Kong, Monaco, and we will have offices, if the COVID allows us, hopefully from the next January, in Madrid. And the company started as a vertical startup focused in marine FGD systems, but from the very beginning, the company opened their portfolio to the renewable technology and solutions to reduce the pollution in the world. We were involved from the very beginning in the Chinese CSP program. We purchased one company that is Engine, that is the former design institute from the Souhan company. So we have all the technology from them. And we created a joint venture with one of the biggest Chinese players, that is Power China, that this give from one part. We have our knowledge and our international resources and way to do the things. And from the other part, we have the amazing muscle of the Chinese state-owned companies, and in this case from Power China, that is one of the biggest construction and engineering groups in the world. Because this presentation we will share, you will have time to go to this. We have different business lines. I am in charge of the Pacific Green Solar Technologies in a worldwide way, not only in the overseas market, but also in the Chinese market. That is really a challenge, but I am really proud of that. And we have also technologies in water desalination, in energy storage system, battery energy storage systems, the FGDs for the marine technologies, and the FGDs for the land power plants. Then, going to the topic of this presentation, really, Luis did fantastic work helping to the development of the PNIEC and helping that on the PNIEC, the Spanish National and Energy Climate Plan, it was included 5 gigawatts of CSP by 2030. The point is that when the first draft of the auction calendar was published on the last November 6, everybody was expecting that probably by 2025, at least the half of that 5 gigawatt will be there. But we had a surprise in the form that only 500 CSP megawatt were there, including in the auctions, not in this year auction, but from the next year auction, and a slot of 100 megawatt CSP per year. This clearly, it was compared with the other technologies, something not fair at all, because they include just about 20%, less of a 20% of the forecasted amount, and the rest of the technologies, they have about 1/3. Then it was submitted allegations, and finally, the official calendar that is in this moment was published on the last 5 of December. They changed the scenario. For the auction in 2020, it will be not in principle CSP. I say in principle because I will come back to that right now. And from 2021 and in the 23 and 25, they will include 200 megawatt per year. Keep one thing in mind, that is that this calendar, it's not stamped on stone. It's a live calendar. What this means? This means that on the auction of the next year, if the ministry see that there is appetite for the CSP and that there are plenty of companies submitting offers, the calendar will be reviewed in a yearly basis. So then probably they will include more CSP in 2022, that right now there is nothing, and they will increase the part of the CSP for the rest of the years. One point that we have in mind is that maybe the ministry, they are very conservative, and they take a point of view that they are expecting a huge market interest for the PV and for the wind, but maybe they are afraid that it will be not so much interest in CSP, that I am sure that will be not the case. And then they prefer probably to be conservative, to put during the first year and a small amount, and then from the next years, in the case that they show that there is interest from the different players, then they will increase the amount. As Luis mentioned it in his previous presentation, nowadays the cheaper way to generate electricity during the day is PV. And when we are thinking about CSP, we need to forget a little bit the old paradigm from the previous generation plants that were designed to try to be as much as possible 24/7. And we need to keep in mind that we will need to look like a new generation of plants, that it will be like, between brackets, the battery of the PV systems. So the plants that we will do, they will charge the thermal energy storage system during the day, and they will deliver electricity in a dispatchable way during the night. The other thing, another of the add values that CSP can bring to the system is the fact that there is about 100, 200 hours per year that are at a peak rate, and you can use the CSP to regulate, to have a reservoir of energy to deliver the electricity when the system needs. And this will avoid that sometimes some crazy prices go to the pool. In an article that our company published about 2 weeks back, we titled that the 4 keys to winning in the Spain World Leading Path for CSP. And I think that these are the main values from CSP. It's an established technology, so it's not something new. In Spain, there are plants that are working fine from more of 13 years back. It have a diverse supply chains, and also most of the supply could be from the country where the plants will be implemented. In this case, Spain, but in other cases, like for example, in the Moroccan CSP plant, in the case of Nord 1, the local content was at 30%, but in the case of Nord 2 and Nord 3, the local content was increased up to 35%. Then we are lucky because in Spain, we don't have an historial of huge mistakes in the plants. The plants are working fine. And as I told you, the plants shall to be now focused on storage. This is what I was explaining to you before. Here, we have the prices, but we are really thinking that the next target, the next key target in the next coming years, probably maybe not in Spain, but yes, in some countries with an amazing DNI, like Chile, it will be LCOE under 50 US dollar per megawatt. One of the points that I would like also to point out is that as an example of the maturity of the technology and the improvements that every year are made in the O&M strategies, is that nearly in a yearly basis, the production of the Spanish actual CSP fleet is slightly increasing in a year basis, but we are not adding any plant to the grid from last 2012. So this means that the technology is absolutely reliable, it's absolutely bankable, and it could be just improving the strategies of the O&M. It could deliver the electricity expected as per the business plan. In a scenario like the one that we are living nowadays, that it's making that some people it's rethinking a little bit about the localization of the industries, because the COVID creates really mainly during the last months a huge drama sometimes in the supply chains. Most of the technology that is necessary for the CSP can be developed here in Europe. I can say that 100%. And also, if you want to diversify that, you have players in different continents, because as you know, one of the key components to reduce the LCOE is the economy of scale. That this is another point that I would like to point out. I hope that on the next revision of the auctions calendar for the Spanish auctions, the ministry will be more brave and they will include more than 200 megawatts for the CSP, because otherwise it will be really difficult to create an economy of scale that helps to reduce the prices. One of the important things, and really what happened in other countries, it's sometimes concerning, but what is happening in Spain, what is happening in Morocco, what is happening in South Africa, and what is happening in China is that the plants have no mistakes and they have full reliability. All of us know that, unfortunately, and for different reasons, that was not the case of some of the plants located in the US. But really, Enrel did fantastic work summarizing and identifying the kind of issues in the CSP plants, and that lessons learned could be easy implemented by any player. And really, we are looking for not only to an Spanish renaissance of the CSP, but we are really looking to be like the lighthouse that will guide other countries to the CSP renaissance. And one of the countries that we have into our strategic plan, and because we are an American company, is the US under the presidency of Mr. Biden. Because as all of you know, the European Commission launched the Green Deal, but also the Biden administration made the statement that they will invest $2 American trillion of US dollars in renewable energies and in the decarbonization of the generation system. And this is what.
If you can have about 3 minutes, it would be fine.
Yes. I will try to accelerate. Thank you very much. I apologize because I am really passionate about CSP. For me, 50 minutes sometimes is like a couple of minutes. So, as it was already commented before, the new generation of plants shall to be focused in a way to achieve the lowest possible levelized cost of electricity, not in deliver electricity 24/7, but in storage the electricity and deliver the electricity by night. Also, it's possible to do an hybridization of these plants, not only with small PV plants that will supply the parasitic consumptions of the plant, that this will help to reduce the LCOE between a 3 and a 5%, but also probably to include on the plants a battery energy storage system that will be able to deliver about half an hour of full capacity of the plant, and this will allow these plants that normally will deliver by night to do cold startups during the day using the best system like a switch on in less of 1 second, and become pickers. That this is an add value also from the CSP plants if we would like to use them as pickers in a way to help to regulate the price of the pool of the electricity. And this is all from my side. I think that I was just in time.
Yes, you were excellent. Thank you very much for this very dense and very passionate and very informative presentation. I think we have the luxury to ask one question for clarification, not more than that, so because to allow time for the discussion. But if there is something immediate that someone would like to ask, feel free to do so. I haven't received any question in my chat box.
Well, I don't know if this is good or bad. Maybe everything was very clear, or maybe there is not so much interest.
It's certainly not the latter. I'm sure about it. I'm one of the least of the most ignorant people in this session about CSP, and I could tell the very interesting parts of it. Okay, let's move to Mr. Luis Crespo, just to not to delay. Of course, he's well known because he participated in the previous session as well. Dr. Luis Crespo, the president of the Spanish Solar Thermal Electricity Association, a former professor at the Polytechnic University of Madrid, and a consultant of governments and financial multilateral institutions. This presentation will be on the future double role generation and storage independent infrastructures of CSP plants and the case in Spain. Great. The floor is yours.
Thank you. Thank you, Theodoros. Thank you very much. And again, thank you very much to the Cyprus Institute and to Manuel and to the organizers for inviting me and giving the possibility for sharing some experience in the first presentation, and now some hints, some very important advice that I would like to share with those of you which are attending the session coming from different countries, because I'm going to explain how we really succeeded in introducing, including these 5 gigawatts of CSP plants in the Spanish national plans for 2030. And this is something that until now, nobody talked about that. So storage means dispatchability, but we don't need dispatchability at all. What we need, our plants are going to play a role which is going to have a specific dispatch profile. We are not going to follow with the demand without a storage at all. No, we are going just to supply what the electrical system need. And by explaining that we are the cheapest option, renewable option, to complement PV after sunset, we felt at a given time that this was not enough. Okay, this was nice, but something was missing, and we wait until the European Commission evaluate the first draft of the Spanish plan, and they ask for more flexibility. So we just start thinking what the storage tanks of our plants can provide. Besides this, in the past time, kind of dispatchability following the demand, but in the future, just to dispatch in the night. And we understood immediately that we had a treasure, a gold treasure in our hands when we have a CSP plant already built. Imagine that the plan includes to build 5 gigawatts. So by building 5 gigawatts, we'll be able to offer 60 gigawatt hours of storage for different purposes, not only for dispatching during the night, but also for dispatching at the specific times when the system needs the most. And I would like to show you, these are typical Spanish plants of 50 megawatts. The storage that you are seeing in the picture have the possibility to store 400 megawatt hours electric equivalent if we are talking about parabolic trough plants, but the same volume, the same amount of salt, molten salt, can store 1.2 gigawatt hours of electricity equivalent if we are talking about putting exactly these same tanks for a tower concept plan. So can you really imagine how much this cost in batteries will represent? This will represent, in case of 400 megawatt, in the range of close to 200 million euros for batteries. And in the case of a tower plant, this volume represent about 500 millions of euros. Imagine which is the savings that we can provide to the system if we can just think not only of dispatching during the night, but offering a second role, which is using the storage for other purposes that the system really are going to need in the future. And so, as I told you, and this has been already explained many times, the primary role of CSP plants is going to complement PV when the sun from dusk till dawn. But the question is, who is going to provide, apart from CSP, this electricity when the sun sets every day? I think there is no other renewable that can supply this kind of specific service at a lower price than CSP plants, and they are not really, until now, battery scales systems, more than 12 hours batteries, and experts don't expect just to have it in coming future. So if there is a market, perhaps they will try to elaborate, but I think the natural role of batteries is just to have a quick response to voltage and to frequency issues in the grid, but not to store massive amounts of energy. For massive amounts of energy, thermal storage is much cheaper than batteries. So the trick is just offering to the system a complete decoupled technology that can decouple completely the collection and the delivery of energy. And this is the case of CSP plants with the help of or by means of our thermal storage tanks, thermal storage systems. But the main purpose of this presentation is just to try to make you understanding which is the second and very valuable role that thermal storage plants can play in the future electric plants of different countries, of sunny countries. I used to say that those countries in the Sun Belt, they have much easier possibility to afford the energy transition than those other countries, like, for instance, Central European countries, that they don't have any possibility to find a renewable system for storing energy. In sunny countries, we have, Spain is one case, but there are many other countries in the southern sun belt of the world that are fortunate because they can just build CSP plants to complement PV and to make a very cheap 24/7 generation system based on solar, in sunny days, but not just looking for 24/7 CSP plants, just looking for a kind of hybridization at system level, not at plant level, but at system level, which is going to be the case because PV plants are going to be deployed much faster than CSP plants. So our role is not just to find or to try to build hybrid plants with PV. Our role is just try to provide to the system the service that the system is going to need in the future. And let me show you one example in Spain of typical case between November and February of the demand in Spain. In those winter days, it is typical that in a week, from Monday to Friday, we are going to have every day at 8 p.m., 9 p.m., 10 p.m. peaks of demand that until now neither CSP nor PV are able to supply, because CSP plants in winter operates because of the remuneration system established in Spain. They don't store the energy to provide electricity during the night. No, they simply provide electricity when the sun shines. And in most of the cases, due to the cosine factor of parabolic troughs in Spain, it is not possible to store any single megawatt hour of thermal heat in the tanks, because the cosine factor is very bad for parabolic troughs in northern European, in other countries, in other southern countries, like it is the case of Spain. So if you just look into the need of storage that a plant delivering night dispatch profile, delivering electricity in the night, is going to require, in case of parabolic troughs, in November, December, January, February, we are going to use only 40% of the capacity of the tank just for storing and dispatching day by day the energy that will be collected by the electric field of the parabolic trough mirror field. That's, you know, we start thinking, lateral thinking, and we say how we can get the most when the storage is empty. Very easy, as our tanks only lose less than 1 degree per day. We can just have more than half of the tank ready for providing a strategic service to the system, independently on whether this day or the previous week would have been sunny or not, because we can store 60%, 70% of our storage without damaging the possibility of decoupling the daily energy and the dispatching energy every day, because we have most part of the tank will be completely useless. So that's, by doing that, we can just provide a strategic reserve. And not only that, if we just simply add electrical heaters, we can just even think of collecting the curtailments of other technologies. For instance, imagine in Spain we are going to have more than 50 megawatts of wind plants in Spain. A very windy day that normally will not be a sunny day, we can offer 100% of our storage capacity to store the curtailments that otherwise will be provoked in wind parks, because in windy days, especially in weekends or even during the day when the demand is not so big, there are going to be more than enough wind production in Spain. So we can just offer that for storing curtailments. And if we are allowed to do that, we can just even think of arbitrating prices. We can just think of buying, independently on which is the case, which one is provoking low prices in Spain, sometimes zero electricity prices. We can just buy this electricity and just store and just delivering when the price is higher, because we don't need the full volume of the tank during most part of the year. So this is something that has convinced the Spanish government to say, okay, just by allowing one CS plant to be built, we are going to have also additional possibilities that can help the deployment of the other technologies, renewable technologies, which are not dispatchable. And just let me just, I'm going just only a couple of slides more, just providing you surprising comparisons with other storage alternatives. When people talk about
you know, 2 or 3 minutes. Yes.
Yeah, electricity storage. We just thermal storage for electricity service, for electricity in the grid, is 10-fold larger than the capacity installed in batteries right now. But when you think of storage of electricity, everybody thinks in batteries. It's not the case. We are 1 order of magnitude larger at this current time. When you are talking about cost, the cost of the storage system itself is in the range of $35 per kilowatt hours, while the cost of battery pack plus balance of systems for battery systems are 10 times higher. You may say it's 10 times higher. No, it's infinitely higher, because as soon as you have your storage already built for the generation purpose of the CSP plant, using the storage for other services costs nothing. So the difference is not 10 times, it's infinite. So we can just offer infinite lower prices than PV batteries for the same system when the storage is already in place. So that is what I said already, curtailment recovery, strategic reserve, and price arbitration. And just giving you an example, the 5 new gigawatts of CSP plants, which we managed and we succeeded to include it in the national plan for 2030, could help to save more than 20 million euros in batteries or new hydro pumping stations. So this is something which has been acknowledged and already recognized by the Spanish government, and that's why these 5 gigawatts are now in the picture for the Spanish plan for 2030. The question is whether this is a kind of inconvenient truth for other technologies, but okay, that's the case. And just the last, well, I'm going to go very, very quick. Julian Blanco yesterday provided a new approach of planning systems using inductive projection models that Protermosolar used in 2018 to respond to the expert committee that was published in Spain, where no further CSP plans were expected, and we demonstrate that using common sense inductive approaches provides much better planning trends and goals than any other system right now. Julian explained very well yesterday, and I recommend you to see his recording, because was very interesting, these kind of things. And just conclusions, again, this is the slogan: buy one generation infrastructure and get one storage infrastructure for free that would cost in batteries or in pumping stations incredible amount of money. So we are in a position to say that we are going just to offer a primary role complementing PV production. We can use the storage for many other things which has not been considered until now, but which are the basis of a smart electrical system for the future. We are wondering whether people talk about hydrogen as a way to as a kind of electrical storage, but I think it's not going to be the case. I don't consider that hydrogen is going to be burned back to provide electricity. It's going to be used for other purposes. That's why I say that power to X hydrogen and back to power is nothing to be, seriously considered. It's going to be seriously considered for mobility or for industrial heat, but not for electricity again. So it's not a kind of storage at all. But power to heat and back to power with CSP plants is the right way to proceed. And as I told you, any transition would be much easier in those countries where CSP plants can be built than in those where this is not going to be possible. And that's all in my side. Thank you very much.
Thank you very much, Dr. Crespo, again for a passionate presentation and a very informative one. I have one question here, but I think it might be better to put it during the panel discussion, so that perhaps it might be appropriate for anyone to ask. I also have something to ask on hydrogen, but let's see later. Thanks a lot. Thank you very much. Let's move to our third speaker, Professor Zhifeng Wang, who will talk about China's pathways for CSP. Professor Wang is from the Chinese Academy of Sciences. He's a founder and chairman of the Chinese National Alliance of Solar Thermal Energy Power. And he works very much on CSP, heat transfer, thermal storage systems, and solar buildings. So, Mr. Wang, it's your turn. Thanks a lot.
Thank you. My presentation is China Marketed Pathway for CSP. I'm Zhifeng Wang, the professor of IEE of CAS. Before this year, I have marketed some timeline of Chinese CSP. We started the CSP project some 20 years ago. In October 2000, we built a 12 meters parabolic concentrator. Then after 5 years to 2005 July, 10 kilowatt de-stirring research in R&D project funded by Ministry of Science and Technology. In 2012, 1 megawatt solar tower built by my laboratory. 2016, 10 megawatt tower with 15 hours some storage built in Dunhuang, city of Gansu province. And 2017, 1 megawatt parabolic trough. This project is also funded by Ministry of Science and Technology. Also, the same year is 2017 June, 15 megawatt new type concentrated CSP as a look-like Fresnel reflector, but not Fresnel, only likely generate power in 2017. Now this system already stopped. In 2017, another very interesting technology is molten short parabolic trough concentrator with power built in Dunhuang Aksai city of Gansu province. The loop length is 800 meters. 2018, 50 megawatt parabolic trough built by Guangdong Nuclear Power Energy Company. 2018, 10 megawatt thermal, only thermal power beam down collector located in Gansu province in Yumen. We will see the next page. You can see next page. You can see the picture of this beam down system. 2018, 100 megawatt tower with 11 hours some storage was installed in Gansu province in Dunhuang city. 2018, same month, another 15 megawatt tower with 700 some storage was installed in Qinghai province in Delinha. It's very high. The latitude is 3,000 meters. In this year, January, 100 parabolic trough concentrator plant built in Qinghai province, also is very high latitude place, about 3,000 meters. 2023 is the next project, 200 kilowatt subcritical CO2 CSP were installed in Beijing. As I have introduced this project in last presentation. Chinese CSP plants connected to grid. We have a total 521 megawatt until today. The first one is you can see the first color. I have made 4 colors. First color is before 2018. The price is very complex. Oh, sorry. First one is 0.31 yuan per kilowatt hour. The second project in 2016 is 1.2 yuan per kilowatt hour. Third is Shouhang Dunhuang Solar Tower, 2016, at 0.31 yuan per kilowatt hour. Second is we started because we started the demonstration 1 megawatt of demonstration projects since 2016 to 2018. So there are 3 commercial CSP plants completed in before end of 2018. First one is Guangdong Nuclear Parabolic Trough is 50 megawatt. Second is Shouhang Dunhuang Solar Tower, 100 megawatt. Third is Delinha Solar Tower plant. The price also is same. The 3 one is same price is 1.15 yuan per kilowatt hour. You can see the trend is another CSP projects have no price, because the first demonstration projects in our policy, you have to build it before, connected to grid before December 31, 2018. If after this time, maybe you cannot get the 1.15 yuan per kilowatt hour. So we have 1, 2, 3, 4, 5 projects installed and connected to grid already, but it's later than 2018 December 31, so they have no price until today. A lot of companies are complying to government. Why don't give them 1.15 yuan per kilowatt hour? Government have no answer. Discussion now have but no answer until today. So that's a pity for this. About 300 megawatt projects have now get the electricity FIT now because they are later. So total we have 11 projects in connected to grid in China until now. We have 8 solar tower, 2 parabolic trough, and 1 linear Fresnel. Okay, that's the Sohang 100 megawatt solar tower in Dunhuang. Dunhuang was a very old city, built in 1,400 years in Tang Dynasty. Silk Road as a main town in Silk Road. The owner and the EPC are the same company as Sohang. So the grid connection is December 28 in 2018. You can see very interesting, just before 3 days to the deadline. If they after 3 days they cannot get 1.15 yuan. Another very good project in China is SuperCon solar 50 megawatt solar tower plants in Delingha. The operator data in this plant is very good. You can see the blue one. The blue one is calculated. Some simulation, different amount of simulation. This green one is really output from the plant. It's as a comparison as a good. It means the plant has arrived the design point, design value of the plant. It's 2018 August, September, October, November, December. It's 2020 January, February, March, April, May, June, and July. And that's output. The third one is Guangdong Nuclear 50 megawatt parabolic trough plant in Delingha. This project has met some trouble in last year and the beginning of this year, but they solved in final. So now it's working well. Oh, this is the Yumen 15 megawatt beam down tower plants. There are 15 beam down towers in this plant, but now they only running operate one tower. This one tower is a 50 megawatt thermal power each tower. The total is 15, but they only operate one tower now. They want to test, after test the tower reflector, secondary reflector, and the molten short receiver, then to develop another 14 towers. Now it's testing now. In 2 weeks ago, one older project, but restart again as a 50 megawatt molten short trough in Aksai. Italy colleague, I think, is a very custom for this project. Some technology import from Italy. The 50 megawatt molten short trough will output 200 million kilowatt hour per year. Sorry, this is not beam now. the location as you mentioned, the same location. Our have some new policy in CSP. In February 3rd, the Ministry of Finance, together with NDRC, National Developing and Reforming Commission, and the NEA, National Energy Agency, has issued a document. The document published the policy at the start, where the new CSP projects are no longer included in the scope of central government subsidies since 2021 and December 31st. If you before this time to connect to the grid, you can get some subside, but if after, it's impossible to get that. Okay, this page is hello.
Yes, you would have another 2 or 3 minutes in order to finish on time. Is that fine?
Okay. Okay, maybe my computer power is not enough. Sorry. Because in China, water as a CSP play a major role in future energy mix in China. Because our green energy in our 2019 to 2013 to 15, our green energy will increase the ratio from now we are about 15%. We are to 15.3%. We are increased to 15% in 2050. So a lot of green energy in west of China, but our industry and the energy load, power load in east of China. So we need to transfer about 4,500 kilometers from west China to south of China. If PV installing here in the winter, everybody know if during the nighttime everything is lost, stop. So solar not solarization. So in this case, in 2015, if we use green energy, we have to some storage or battery. But the battery, the price now is very high. Just Louis issued the price of a battery about $815 per kilowatt hour with a frequency adjustment. But our sum storage only $15.7 per kilowatt hour if we based in China, in Gansu, some 12 hours CSP plant. The sum storage part only about 10% to the battery. So I think in the future, if we transfer about 5,000 kilometer energy from west of China to south of China, have to use the cheap green energy. It's only cheap green energy as I think as CSP can support energy continue. In next generation, I think maybe CSP will plus PV make a hybrid solar plant. That's our future. I think is the future. As if only CSP plant price some look like a very high, 4 times or 5 times than PV. If we maxed, then can stay the output and get a low price for the user. Thank you for your attention.
Thanks, Professor Wang. This is really interesting, and perhaps we may have the opportunity to exchange also views between the European and the Chinese experience between the speakers. I have a question which is a European one, so it is for our European speakers, more or less. From we may come back to the Chinese situation. There is a question: does the European Green Deal or the Spanish PNIEC, I suppose that's the National Energy and Climate Plan of Spain, I suppose, do they mention how to tackle storage or flexibility issues? I suppose the European Green Deal does not specify technologies, but perhaps you could talk. It was mentioned, I think, in the previous session as well. But since the question has been raised now, is there any specification about how to tackle storage flexibility issues?
Well, if my from Spain, all right, Green Deal is something that applies for the whole European member states, but generation, the generation fleet and also the storage fleet is something that depends exclusively on the countries. So I think this is defining which is the mix that each country is going to have by 2030. This has been already submitted, and this has been already commented and approved and suggested some changes in case of some countries. In the case of Spain, they say that the plan was very ambitious, and they applaud the presentation of the Spanish plan. All that we have to do with the storage, there will be perhaps some European regulations that may especially for research and development, that perhaps can support specific demo plans or specific research activities in one way or the other. What is going to affect the countries is the directive for the electrical market, the directive for markets, and this perhaps can also affect to some extent which is the role that the storage can play in either country. In Spain, we can use batteries and also thermal storage tanks, and I think that either way, no matter which is going to be the European regulations, I think that we are going to find a way in which the thermal storage system are going to play a very, very important role in Spain, perhaps not in the coming 2, 3, 5 years, but when we start to stop, to close all the still remaining coal plants, the still remaining nuclear plants, and most of the combined cycles, it's when the need of storage is going to be a must, and there will be no other choice and no other cheaper choice to cope with the needs of the system for massive storage of energy than using CSP plants and thermal storage from CSP plants.
Okay, that's clear. Thank you. Mr. Lara, perhaps not necessarily about Spain, but the broader policy context.
Yes, I have my thoughts on that. I think that for short-term storage, it's very clear that the best option are the battery energy storage systems. Then for all-night storage, or even for few days or also a few weeks storage, because the thermal losses in a thermal energy storage system in a test is less of 1 degree per day. It will be the test. But also I would like to include into the storage what we are calling the seasonal storage. So storage for seasons. And for that, we are really thinking in the green ammonia. And also to generate green ammonia, you need a chemical reactor that need to be on 24/7, and the best for that is during the day you supply electricity by PV, but during the night you have the CSP for that. So it's another value that you can use the CSP to manufacture green ammonia.
Great, thank you. There is a related question about thermal energy storage by Fernando Oliveira, asking why is it not being fully used for process heat in European industries? For example, in ceramics, in glass, in cement. Can you comment on it?
Well, I can say something. I don't think whether the question is related to storage or related to CSP, because the first step is to collect, to gather the energy. And I think, well, the question is electricity, as I say in my previous presentation, this can be produced here and delivered and consumed many kilometers away, while the heat is not the case. And so the possibility to have centralized heat in large areas of industry, we can think of some kind of central thermal network. And in this regard, perhaps big or large, or not as big as plants, CSP plants for electricity production, but big enough. I mean, this can be conceivable. But normally, this kind of service is going to be delivered in a distributed way. Every single factory that want to make use of solar energy for thermal purposes, they have to think, how much surface do I have in my rooftop, whether I can put something in my rooftop or whether I can put something aside because the land belongs to me. And this is not, I mean, there is always, I mean, constraints in size limitations. And also, unfortunately, as you are just, I mean, getting rid of too much surface to place large plants, I think storage, the best way is just to, I mean, to deliver heat whenever the sun shines, and just to save or I mean, to not to burn gas at the time that the sun is shining. But after that, I think it's until now much cheaper just to say that the CSP will provide a 20, 25%, 30% of the total consumption, and you don't think in storage at all. Just you have another backup system, because backup system is always needed for that purpose. So I think you have an industrial process for producing something, you can stop it. And I think is until now, as you don't have very large surface, thinking in storage for this kind of applications, in my opinion, is not, maybe some cases in which you can find that the storage really fit with the needs of the customer. But most of the time, you are going to build a CSP plant for thermal purposes to deliver or to save 20% of the total consumption, thermal consumption of the factory, but no more. And in this case, storage is not really a real solution for that.
Okay. That's very interesting. I think
yes, I was about to ask.
Okay,
we can hear you.
The both direction charge from grid and the discharge thermal to generation power to grid. Both direction is interesting for the CSP plant, but the battery cannot both sides charge. You can charge from grid if in the energy peak, energy output peak, and then we can discharge the thermal to generate electricity, then to support energy power to grid.
Yeah.
And to balance the grid.
Yeah. Okay. Thank you. I have another question from my colleague Nestor Phylaktos on hydrogen, the relationship with hydrogen. There will be, I think, some presentations later in the next session, but still, would you see that there would be a future of utilizing CSP for directly producing hydrogen? Because what we now mainly think about green hydrogen is that it goes through the production of electricity and its use in electrolyzers. But perhaps this may not be the most cost-effective option for CSP. Would heat be used in a useful manner to produce hydrogen from CSP?
Well, the thermal path for producing hydrogen has been explored, and not only for producing hydrogen, for producing synthetic fuels as well. And well, I don't know. I think, as Javier already said, production of hydrogen for either for synthetic fuels or for green ammonia needs that the electrolyzer will work, I mean, hopefully 24/7 or at least 8,000 hours per year. And in this regard, I think the combination of PV plus CSP can provide this possibility. PV during the day and CSP during the night, so you can have perhaps not 8,000 hours, but you can reach very easily 6,000 hours or 7,000 hours with a combination of CSP plants with PV. But other possibility is just that you can also get, you can have a very cheap PV factory, and that will produce only 2,000 hours per year, because this is a typical rate of PV plants in Southern European countries, and the rest you can virtually buy from the grid with bilateral contracts in green for green technologies as well. So you don't need just to have a backup with CSP. If this kind of green hydrogen, it may be possible to be produced with PV plus the grid, provided that you have contracts with 100% grid supply of green renewable energy. I don't know. I think, well, this is a kind of trick, but if this trick function, I think there is no role for CSP complementing PV for this specific purpose. But I think if you are just thinking of a factory that will produce with the certificate of origin, physical certificates of origin, 100% green hydrogen, and I think in this case, combining in a single unit PV plants and CSP installations may be a solution. Yeah. I don't know, Xavier, what did you think about it?
Yeah, we did some numbers for different countries in the Gulf area and also in Chile. And for us, the lowest levelized cost of green hydrogen, it was just to produce the hydrogen with electrolyzers during the day, feed by PV plants. But the point is that the hydrogen is not easy to transport at all. So if you want to export that energy, you don't need hydrogen, you need ammonia. And when the ammonia enters into the equation, then the best technology to run 24/7 is hybrid plants of PV plus CSP. So then I can see a very brilliant future for the CSP in the production of green ammonia. If it's just hydrogen to do the consumption of the hydrogen, let's say next door, then there is not so much room. But if you want to move that raw material in the form of ammonia from one continent to the other, then the CSP will have a huge role. And it will be, under my point of view, a key factor in the development of the green ammonia industry.
Yeah. The question is whether this green ammonia or green hydrogen is going to be considered to be a storage for producing electricity again. And I don't think that, I think most part of the hydrogen of ammonia are going to be used for other purposes. So in this regard, so you can use it, but you can have a fuel cell and things like that. But I don't think that in the future, I think the green ammonia or the will is going to be used for fertilizers, and the hydrogen is going to be used for mobility or for industrial heat for final uses which can be electrified. So for those uses, perhaps green hydrogen is going to be interesting. But I have a lot of doubts that power to hydrogen and back, or ammonia and back to power is going to represent a huge amount of storage in the future. So I think it's a way, it's another final user, it's another demand for CSP electricity, but not to be considered.
But I am thinking also that, for example, sorry.
Yeah, go ahead.
No, thank you. I was thinking also that, for example, the green ammonia will have a very important role in the decarbonization of the maritime sector, because the ships can run directly with green ammonia, not with fuel cells, but burning the ammonia.
Yeah.
And without any emission of CO2, obviously.
And I think
what would be the Chinese perspective?
Okay, my idea is the hydrogen may be a philosophy question. Everybody knows storage is very complex and expensive, but 10,000 billion dollar invest already. Nobody know why. The question is very philosophy.
Okay, thank you very much for this very informative, very comprehensive, very passionate session with presentations and also very good discussions. And thanks also for the participants who participated in the discussion through this indirect way, through the questions. I think there is a short break, and then we will give the floor to the next session, to be chaired by Dr. Simona de Iulis from ENEA, the Italian National Agency for New Technologies, Energy, and Sustainable Economic Development. Is that correct, Manuel? So we
Yes, it is
got to
5
start in
minutes break.
6 minutes.
Bye, Luis.
5 minutes.
Bye.
Thank
Bye.
you.
Thank you.
Ladies and gentlemen, good afternoon or good evening or morning, depends where you are. Welcome to the fourth session of the second day of the CSP4Climate International Conference. I'm Simona De Iulis from Solar Energy Research Scientist at the Department of Energy Technology and Renewable Energy Sources of ENEA, the Italian National Agency for New Technology and Sustainable Economic Development. I'm honored today to chair this session, and I would like to thank the Cyprus Institute for this opportunity and the European Union for funding the System Horizon 2020 project. This is we'll go through hot topics and trend topics today. We will see not just the usage of concentrated solar thermal technology for producing electricity, but also for producing heat that can be used to produce commodities such as hydrogen, but also we see an optimization of energy system design in a way of an integrated approach with photovoltaics, but also two types of storage system, so thermal storage or battery energy storage. And at the end, we will see a best case study on best practice studies on how can we improve the reliability of concentrating the solar plants in terms of performance. So I'm going to give the floor to the first speaker of today, William Hamilton from National Renewable Energy Lab of United States, Golden, Colorado, and is going to give us a presentation on dispatch and design optimization of CSP system hybridized with photovoltaics, and has joined NREL in 2019, working at the Thermal Science Group, and his work is on the development of models to evaluate performance and optimize design, dispatch, and operation of concentrated solar power energy systems. So William, the floor is yours. I think you recorded the presentation, so maybe the organizer can
Hello, I'm Bill Hamilton, a postdoctoral researcher at NREL, the National Renewable Energy Laboratory located in Golden, Colorado. Today, I will present a subset of our work investigating dispatch and design optimization of CSP systems hybridized with photovoltaics. Let's begin. Here, I am presenting an outline of today's discussion. I will start by discussing a bit about CSP PV hybrids and our simulation methodology. Then I will share some specifics on dispatch and design optimization and present a case study on designing hybrid systems for a market price signal. Lastly, I will draw some conclusions and discuss future developments of this work. Here I am showing a world resource map of direct normal irradiance. Now I am highlighting the places with high solar resource, which enables early adoption of CSP technologies. While these locations share a common factor of high solar resource, each location has its independent considerations. For example, the electricity market, which must be accounted for by a technology developer. I believe this is a major hurdle for adoption of CSP. In addition, because DNI is a major contributor to the location's global horizontal irradiance, locations that are attractive for CSP technologies will inherently attract photovoltaic systems. As a result, combining CSP PV systems and taking advantage of subsystem strengths could provide an advantage in the market. Some of the strengths of these systems are listed on the right. Here I am depicting what a CSP PV hybrid might look like. However, there are multiple configurations that exist in literature. The work that I am presenting today focuses on tower technology. However, we have some work planned to perform similar analysis looking at parabolic trough technology. While these systems are interesting and could provide value to the grid of the future, They are difficult to simulate because they are so customizable. CSP PV hybrid subsystem sizing can be challenging and time-consuming. The design process might have a set of constraints that are very specific to the individual project. From these, engineers will make some high-level decisions based on prior knowledge or rules of thumb. They then simulate the system, which can be particularly challenging to handle subsystem interactions. Then they analyze the results and determine if the design meets the specifications or the profitability metric. If not, they iterate on the design variables, which can be time-consuming. Only after the initial design phase is complete do they move on with the project. To simulate CSP PV hybrid systems, we implement System Advisory Model, or SAM, which is developed by NREL to handle individual subsystem performance characterization. We start with high-level system design variables, such as the size of the photovoltaic field or the size of the CSP system, etc. Next, we export the subsystem performance to data files, which will later be used by our dispatch optimization model to make operational decisions. Then, when simulating the CSP system, we solve a rolling time horizon using a 48-hour forecast every 24 hours until the annual simulation is complete. Our hybrid dispatch optimization model is a mixed integer linear program, or a MIP, that maximizes the profit over the time horizon while accounting for O&M costs associated with various operations. Once the simulation is complete, we do some post-simulation calculations to pull everything together before running SAM's financial models. This is just an overview of System Advisory Model, or SAM. SAM contains performance models and financial models for renewable energy systems, for example, CSP and PV systems, but not them together. There is a lot of work happening at NREL that utilizes the core models within SAM. Thus far, we've formulated the CSP PV hybrid dispatch optimization model to handle 10-minute time steps. Currently, we're working on multiple projects to increase the time fidelity while maintaining problem tractability. Here is an example of the output of the dispatch optimization model. In this figure, we have gross power on the primary y-axis, thermal energy storage or state of charge normalized on the secondary y-axis, and time on the x-axis. We can add the price signal that we want the system to dispatch against, shown in black. Next, we can add the photovoltaic generation. And finally, we can add the battery operations, charging, discharging, and state of charge. From this, you can see that the battery is peak shaving photovoltaic generation during winter operations. However, in the summer, we observe that the battery is being utilized to increase system production up to the imposed limit, which in this case is 100 megawatts, when the power cycle efficiencies limit production due to high ambient temperatures. From my previous descriptions, we can characterize CSP PV hybrid systems with design simulation, which utilizes dispatch optimization to control subsystem operations, shown as a black box here. From this, we can change a set of design variables x to get a response of interest f of x. This response could be a financial output like power purchase agreement, or PPA, or levelized cost of energy, LCOE. It also could be a performance metric like capacity factor. We then can iterate on this process using a derivative-free algorithm to minimize or maximize the response of interest. In this case, we use NLOpt, which is an open source Python library containing multiple gradient-based and derivative-free optimization algorithms. However, due to the nature of the problem, this methodology has limitations. Depending on the design space, the solution could be sensitive to the guess value, which may require initial sampling to overcome. Global optima is not guaranteed, and it's difficult to prove, and there could exist multiple optima. Lastly, this process could be computationally expensive depending on the required time for each iteration. However, in practice, this method has provided insight on practical engineering solutions. In the next couple of slides, I will present a case study that investigated CSP PV hybrid designs under 4 market pricing scenarios, which will be presented in the next slide. Here, I'm presenting the design variables lower and upper bounds, as well as the initial values, or base case, for both CSP and PV subsystems. Our objective of the study was to minimize PPA price and a penalty for exceeding flux limit. PPA price is the price at which the system can sell electricity and be profitable, assuming that the price can vary based on a schedule that was predetermined. PPA price is calculated based on the system simulation, which is a function of the dispatch optimization. The maximum flux experienced by the receiver is a function of the receiver and the design, heliostat field design. We impose this constraint using a penalty factor in the objective, which minimizes the violation of this constraint. Below, we have the 4 pricing structures I alluded to before. You can see that each one has peak prices that are typically occurring in the evening. Our dispatch optimization model will target these prices to dispatch energy during the highest value time periods. In the 4 cases, we saw NL-opt algorithms improve PPA price by 16 to 23% while enforcing the maximum flux constraint. Note that the 2-tier market resulted in the lowest PPA price in just below $60 per megawatt hour. The 2-tier market price is interesting because outside of the peak price, or the base and peak price window, the price is 0. Here are the optimal design variable values for each market structure. The general trends that we observed were that the optimal power capacity was 150 megawatts, which coincides with the lower bound that we provided the problem. The CSP systems resulted in a solar multiple close to or less than unity, which is significantly lower than the results in literature that minimize LCOE. Minimizing LCOE tends to produce a baseload configuration where the CSP system has a large solar multiple. And lastly, the photovoltaic field capacity was greater than the imposed 165 megawatt transmission limit, which resulted in curtailment during high solar resource days. In addition, these optimal designs resulted in an estimated installed cost of $700 to $900 million and capacity factors of 50 to 62%. Note that I am defining capacity factor here by the grid transmission limit and not the combined capacity of the 2 systems. By aggregating each sample design, we can generate Pareto frontiers between the objective and another performance metric of interest. This enables us to understand the trade-offs between 2 different objectives. Here I'm presenting the trade-offs between PPA price and capacity factor for each of the 4 markets. From this, we can observe that the 2-tier market PPA is sensitive to increasing capacity factor, while in the PG&E and CAISO node market, there exist designs that could increase the capacity factor as much as 10% with relatively low impact on the PPA price. Today, I described CSP PV hybrids and discussed some of the challenges regarding simulation of these systems. I presented a small case study on the design optimization and showed that minimizing PPA results in smaller CSP systems than minimizing LCOE. Lastly, I showed that Pareto frontiers can present trade-offs between 2 metrics of interest as a post-optimization sensitivity analysis. In future developments, we would like to integrate this software into a publicly available tool. Currently, we are planning to integrate this new capability into the new open source HOP, or Hybrid Optimization and Performance Platform. Additionally, we would like to improve the design problem tractability by using some data clustering methods that can limit the number of days that you have to simulate in order to provide annual system results. Lastly, we would like to explore other objective functions based on stakeholder interests and explore the trade-offs between day-ahead participation and real-time market participation. With that, I will conclude. Thank you.
Thank you very much, William. So interesting technically also to follow all these simulation. I will keep the time for the question and answer at the end of the session. So I will give the floor to Christian Sattler, that is going to talk about hydrogen and solar fuels. Christian, that's working as acting director of the Institute of Future Fuels of the German Aerospace Centers, DLR, and also professor at the Technical University of Dresden, and he spent his career on study on concentrated solar thermal technology to produce solar fuels, I will say. Thanks.
Thank you, Simona, for this nice introduction. And now my topic is hydrogen and solar fuels. So what this has to do with concentrated solar technology. And for us working in that field, it's obvious to not only use the solar generated heat just to produce power, but to use it for thermochemical processes, as the efficiency of such processes is much higher than the power production, and therefore it could be a well to establish energy source for a number of processes. And there are conferences of this. One example is the High Temp forum that happens in Adelaide every other year, about which combines industry of that area where this high temperature heat is needed with the people from CSP, and there we discuss how to go on with these technologies. In general, solar heat is rather cheap, so it's less than about 1 euro-cent per kilowatt hour, and it can be used to produce solar fuels like hydrogen, like synthesis gas, like methanol or kerosene. But it also can be used to produce chemicals like sulfur or ammonia, or materials like cement, phosphates, or several metals. And it's even good for high temperature thermochemical energy storage to generate constant heat coming out of the storage system, which might be of very high value, especially if you couple it to other chemical processes. It's actually already established in the CSP community that such technologies have a high value for the industry. So the German CSP Industrial Association, DCSP, just wrote a position paper on how green hydrogen from desert areas of the world can help to improve climate, and therefore it is of high relevance for future fuel production to use CSP for that. I mean, in the last session there was a nice discussion where Luis Crespo and others discussed what is the benefit, and obviously the benefit is to have the cheap heat storage to operate such systems 24/7. So the technologies to produce large amount of energy for such technologies, for example, to operate electrolyzers, is there. However, there's still some R&D needed to get the other technologies that are not established in such large dimension already, like thermochemical water splitting, to the level that it can provide the necessary chemicals for industry to a price that is attractive to change the technology. The study is available online. You can get the slides afterwards and look if you see that. I think they also will make it in English. We see a nice development over the last 5 years. So I'm working in that field for about 20 years, and the first 15 years were rather slow and calm. But after the COP21, we see an increasing interest into hydrogen. At COP21, the Hydrogen Council was formed by CEOs of large companies. And the vision of the Hydrogen Council is something that everyone in industry and also in research should take seriously, because they say in 2015, 18% of the final energy demand will be provided by hydrogen. It will abate about 6 gigatons of CO2 annually. About $2.5 trillion will be the annual sales value for hydrogen and the equipment, and about 30 million jobs will be raised. So maybe it's too optimistic, maybe it's not, maybe we will get even beyond that. Anyway, it's a big market, and CSP can provide a share to that. So what we also see in 2020, so today, that many countries developed strategies how to get into hydrogen. In Germany, we have a national strategy and a National Hydrogen Council. In Europe, we have the Green Deal, we have the European Hydrogen Strategy, we have the European Hydrogen Roadmap, we have Clean Hydrogen for Europe as a private-public partnership to develop the technology. And we see this globally in many countries that we are on the way. It is always an important part of all these strategies that hydrogen needs to be green as soon as possible. Of course, it has to be started, but we need to be green early. So another argument to establish CSP in that area. The Japanese were actually the first to mention hydrogen as their main energy vector for the future. And it's interesting to see, if you transfer an energy system like the Japanese, how much hydrogen is necessary and how much solar radiation need to be transferred into the vector hydrogen to provide the necessary amount. And a car only needs about 100 kilograms per year. But if you run a gigawatt power plant, it will need something like 200,000 to 400,000 tons, which is equal to 2 to 4 million fuel cell vehicles. And as you see, the Japanese energy mix in 2013 has something like 300 gigawatt electric. So a lot of hydrogen has to be transported to the areas where the energy is needed. And the same is true for Europe. So we need a lot of hydrogen, and we will not be able to produce it in Europe alone, because the area is not enough to provide this amount of energy. We are already at a certain development level that maybe is not known to everyone. So there is a demonstration project already between Japan and Australia, how to provide hydrogen over long distance by vessels between Australia and Japan. And the ship on the lower right is real. It's in the harbor of Kobe. It was launched last year. Its name is Suizo Frontier, and it's able to carry about 8,000 tons of liquid hydrogen between Australia and Japan. It's in the final stage, and it will probably start its operation early next year to provide the hydrogen. In this project, hydrogen is produced by brown coal. However, in the future, this will be the source will be solar. There is enough renewable energy in Australia that could provide hydrogen for maybe even better prices than brown coal, plus the sequestration of the CO2 will be able to do so. So a big market for us coming from the solar business. Solar fuels is actually not a new topic for the CSP community. When the worldwide community was formed, it was always an issue how to use solar energy to provide fuels. And already in the 1980s, rather large plants were tested on site. So this is an example of the ASTRI project that was operated on the Plataforma Solar de Almería of CIEMAT in Spain, together with DLR and Steinmüller. A 180 kilowatt solar reformer was operated to produce synthesis gas out of natural gas. And the development started from there. There was a time between the 1980s and the 2000s where not much happened. But after that, it started off again. And the question was, how can we not use carbon in this development? So the direct spitting of water came into the focus. And of course, you can use solar energy to produce power and then use the electrolyzer to produce hydrogen, but you have to get over this this hill or this mountain. Instead, you could use the direct way, where you just use the heat and do a solar thermochemical water splitting, which will bring you to the same result. In the end, you have hydrogen plus oxygen, and you will see that both of these molecules have a value for industry. The development, as I mentioned, was rather slow in the first 15 years until 2015. I have as an example the Hydrosol project here. starting off in a small solar furnace with a few kilowatts, then going on the solar tower of Tiamat in the Protermosolar with 100 kilowatt, then designing a megawatt plant as a model, then develop this on the tower again in 750 kilowatt, and then COP22 happened, and you see there were always few partners involved in these projects, but then we got the actual project, which is funded by the Fuel Cells and Hydrogen Joint Undertaking in Europe, and we got a lot of partners, and we got a lot of industry partners in this project, and now we would try to show especially that these technologies are reliable and can be operated for a long time and many circles, and we think that it is possible in the next few years to scale it up even to a commercial level. We should look on other commodities or other chemicals as well that are important for industrial needs and for many other products in the world. And one of them is sulfur. Sulfuric acid is one of the most important products in chemical industry, and it is produced normally by splitting sulfuric acid or dirty sulfuric acid to produce SO2 and water, or by burning sulfur. And we can integrate this using solar energy to do so. And in the meantime, we can also produce sulfur by the disproportionation of the SO2 that is produced, that then can be combusted, heat can be generated, and power produced. It's a high energy process, which is very well for the production of the material sulfur, but also for the production of high temperature, high value heat at a constant temperature level. There were already business cases developed by industry, and it's now the time to get them into real and find where these industry can use this ideas. And presently, the technology is in a level that the 2.5 megawatt Centrec receiver that we operate in at DLR can be used to provide the heat for this process. So we are at a certain level that is ready now to go to the next scale and have an industrial demonstration of such processes. As the last thing I would like to mention, coming from the other side, that heavy industry is very much looking on these processes and is very much looking on how to integrate solar thermal. There is an initiative in Australia, the Heavy Industry Low Carbon Transition Cooperative Research Center. It's on the second stage of the proposal. We hope that it will be realized, where industry thinks for the production of iron or aluminium and alumina or other metals like copper, nickel, or gold, to use these products, to use solar thermal energy, to produce, to use hydrogen, and to use something like the sulfuric acid and the oxygen that we get out of the processes to clean up the technologies for the future markets. So our future vision as the solar people, how to integrate it, is that we take the sun, we take the concentrated solar facility and use resources like water and air to produce CO2-free or CO2 neutral fuels like hydrogen, like synthesis gas, like liquid fuels, especially kerosene for running aircraft, polymers, of course, but also with the nitrogen from the air, ammonia, and as I'm from DLR, I have to say rocket propellants, as rockets are part of our business. Thank you very much.
Thank you very much, Christian, for this nice overview of all the application of concentrated solar thermal technologies to produce synthetic fuels. And we will go through the question later. And now I'm pleased to welcome Price with its presentation of the report on concentrated solar power best practice study. Hank works at Solar Dynamics, company in US, and cooperates with the Manuel, and he is all his career work as an engineer in the concentrated solar thermal plants, and he knows all the commercial plants in the world. He visited a lot of them, and then he studied the performance of these, and he came up with this report that was the first time that I saw was very interesting for me to see the results, and I gave the floor to Ank, and thanks.
Thank you very much. It's a pleasure to be here today with you to share sort of an overview of the results of this CSP best practices study. When we began this study, the first CSP plants were nearing the end of their 30-year contracts, and the next generations of CSP plants in Spain, United States, and around the globe had been in operation for as much as 10 years. And so it seemed like a good opportunity to try to collect information about the operating plants and share it with the industry. The goal of this study is basically that to collect best practices and lessons learned from the engineering, procurement, construction, commissioning, and the O&M of existing CSP plants around the world, and then to share those lessons to help developers and people building and operating plants avoid issues that had been problems for plants already. And so the audience for this is primarily developers, investors, financiers, EPC companies, utilities, O&M providers, and policymakers. And also to identify any issues that still remained, maybe for some additional R&D. Our team is the project was headed up by Mark Mijos from NREL. It was due to Mark that he went out and got the funding agencies to fund this effort, and he pulled together this team. The effort was primarily funded by the U.S. Department of Energy, the Solar Energy Technology Office, and so you can see the team is a group of a good diverse group of experts, but they are largely American for that reason. That was funded by the U.S. Department of Energy. We also had some cost share funding from the World Bank and Solar Paces and some other partners, Estella and Nepri, on the project. But even though we were largely U.S. team pulling the report together, we had a great interaction with a good international collection of participants in CSP. And most of the major participants in the study who provided input to the project. You can see it contains EPCs, independent engineers, developers, vendors, people from many of the plants around the globe. And we also visited a number of plants. And for this study, we really focused on parabolic trough plants and central receiver plants, and really focusing mostly on molten salt technology. It's worth mentioning there are over 90 CSP plants have been built and in commercial operation around the globe. So it's a pretty big milestone. We're approaching 100 operating CSP plants at this point. So the report, as I mentioned, focuses on parabolic trough and molten salt tower technology. We also talk about the operations and maintenance experience. And one of we went into this thinking mostly about technology issues, but what really became clear very quickly is basically over half of the issues raised that we captured were really related to project organization and project execution. And so that was probably an important finding that sort of shows up in the results. So in general, CSP plants are relatively complex power projects. And so what we found was that, actually more of the issues raised were related to the implementation of the projects rather than a specific technology. it's really important to work with experienced teams, and it's important for the team to be very involved and knowledgeable on the technology. Some of the more significant problems experienced were actually with conventional equipment in the plants, and this was often things like heat exchangers, valves, pumps, instrumentation, and heat tracing. The other probably key finding is that the plants really need to be designed for good, high reliability, and because these plants start up and shut down every day, really need to be designed well for off-design operation, especially those during startups. Many times these projects are under difficult cost constraints, but oftentimes efforts to save costs end up being more expensive in the long run. So it's important to make sure you don't hurt yourself by trying to save money. And interestingly enough, performance modeling has not always been adequate on these projects, and that's an area that more effort needs to be made in correctly modeling transient operations, startups, intermittent clouds, and so forth. Okay, so with trough technology, we found it appeared most trough plants were reported as operating well. The solar technology is generally very mature. There's been a globalized supply chain developed, so there's a lot of different vendors for key components. Some of the areas where issues had been identified, an issue with hydrogen coming from decomposition of the heat transfer fluid, causing premature loss of vacuum in receiver tubes in some plants. The collector interconnection with ball joints or flex hoses, still remains a challenge in many plants. Some plants have had problems, as I mentioned, with heat exchangers, both for the steam generation system and the thermal energy storage system. Control systems are sort of not fully state-of-the-art. More effort needs to go into developing improved control logic, automation, and alarm management. And there's a need for standards to be developed for wind loads, collector optics, and similar. In looking at how plants are planned to be used in the future as more of a nighttime peaking fill-in between, at nighttime, probably the process design should be rethought a little bit. Okay, in the case of molten salt tower technology, the successes here, they've demonstrated good reliability generally at many plants with the heliostats. The receiver performance, especially in molten salt plants, has met expectations, so that was a concern. And the long shafted salt pumps have worked well and been very reliable for the most part. Some of the areas of concern, although the heliostats have been reliable, the accuracy at some plants has needed work. Probably the major issue has been the reliability of the salt hot tanks. More focus needs to go into the design of the tank foundation and the overall process design. Steam generator reliability has been a problem at some plants. It's a little more difficult running a molten salt steam generator than a HTF steam generator. Heat tracing is a known issue. It's always difficult, and it just needs to be paid attention to. Make sure there's good design and quality control on the installation. Valve reliability, this has actually been an issue both with trough and tower plants, and especially related to salt valves. And again, control systems could definitely still use some work with the molten salt tower technology. Next in O&M, some O&M, often O&M isn't fully budgeted adequately, especially maybe to get the O&M organization mobilized early in the construction phase and be prepared to start operating at time of commercial operation. It's definitely helpful to have an O&M team with strong prior experience, and having people from the O&M involved in the design, construction, and commissioning of the plant is typically usually very helpful. As mentioned, the O&M needs to really be ready to take over at commercial operation. Training is really critical to make sure the O&M team is trained to take over, and many projects have relied on the EPCs for training, and it's important that although that training is important and often needs to be done better than it has been, the O&M organizations really need to take responsibility and make sure that all their staff are appropriately trained. They should be involved in the manual and procedure development and make sure everything is basically ready. All the systems are ready to take over at COD. And as always, especially in plants that cycle like CSP plants, water quality is a critical element. Okay, in terms of the project organization and execution, some of the key findings really are that the owner's role is really critical in these projects. It's really important to have an owner that's knowledgeable about CSP technology. And that's really the owner's team in particular. The owner needs to make sure they have a good owner's engineer, and helps to have a good, smart, independent engineer that understands the technology. The owner's team needs to be very involved in all phases. The projects that have done best have typically had very engaged owners. And one of the key things identified is it's really critical that the owner provides a good technical specification for the project. The EPC contractor is also a critical element in this. It's clearly best to find an EPC contractor that's got a good proven track record in quality, cost management, schedule, and that's even more important than having prior experience with CSP, although having experience is also really important. The EPC contract is really critical to make sure it's well done and covers all the elements that need to be done, especially things like dispute resolution and payment structures, and one of the areas is in the final acceptance testing. The initial and final acceptance testing needs more thought, probably needs to go into that in most cases. From the project side, this trade-off between capital expenditure versus operating expenditure has been an issue. There's always pressure to minimize CapEx, which means the operating costs tend to go up. And so that's been a difficult balance sometimes. I think we found that remote projects have been more challenging than maybe you initially expected. That's not to say they can't be done, but a lot of thought needs to go into that. It is much more difficult having remote labor and trying to get services and getting qualified staff in these locations for the duration. And as I also mentioned before, solar resource assessment and performance modeling have often been sort of inadequate and could definitely be improved. So basically in conclusion, there really are few remaining technology issues for both parabolic trough and molten salt tower technologies. What remains are really design issues and can be resolved with appropriate engineering and equipment selection. It's important that plants be designed for the transient behavior they'll see. And these projects are complex, so they need to be properly managed, and it's really important to make sure you have a good team that's experienced and can do that. The O&M is critical, and it's been found to be very useful to get the O&M organization involved early in the projects. Accurate wind and solar resource assessment of the site is essential. A number of projects have had issues either with incorrect solar resource assessment or not really understanding the wind conditions at the site. And so based on our findings, we're pretty confident that future tower and trough plants can be built on time, on budget, and perform as expected. So thanks for your time, and here's a reference to the NREL report that was published last summer, and it's available on NREL's website for free. Thanks.
Thanks a lot, and I recommend the audience to download and read. And now I'll open the discussion. I have several questions. I receive also questions. So I will start with the electricity. So the younger from William. I have a question from Chuck Asher that he presumes that the CSP factor multiple is small in the hybrid plant because CSP electricity is only being sold into small time windows with a high electricity price. If this is correct, the question is, how does the PPA price of the hybrid system compared to a PV-only system with optimum battery storage? Do you know the price?
That's a great question. Unfortunately, we haven't been able to do that analysis. So it's one of the things on our to-do list is to compare with just just a PV battery system. That analysis is very sensitive to what your assumptions are about battery costs. But yeah, we do plan to do that. And he is correct. The CSP is dispatching during the high revenue time periods for a short period of time, and they're using all of the day to store the thermal energy storage. So yeah, sorry not to have an answer to that question.
Okay, and do you know when the hybrid optimization performance platform will be public available, the tool on a website, what you present and conclude in your presentation, roughly?
Yeah, so the TRA system, we have a project potentially starting this year to get a TRA hybrid system with photovoltaics into a publicly available source tool that should be sometime mid next year, 2021. We still have to bring the tower system over. And right now we don't have a solid funding resource to bring that into a publicly available tool. So it's undefined.
Okay, so you should have been before in a couple of sessions before that when the DOE was presented and asked money for funding this work. Anyway, and just to keep to keep the electricity, otherwise we go through the hydrogen and we will end. I would like to know from Hank, which is the main difference from the observation that you have from performance point of view of plant that you visited in Spain compared to the plant that you visited in the United States? Because Javier Lara, in the previous session, he pointed out that we didn't have in Spain any performance troubles. So I would like to ask to you, well, which is the reason? Thanks.
So I think that's a little bit incorrect, unfortunately, but there have been some issues in Spain. It's just not, it's in many cases just not as public. There was a big issue with the one molten salt tower project in the United States. That project suffered from scale up issues, probably would be the best way to say it. The scale up was too large, and they really didn't understand the implications of the problems with the thermal storage system. And that's really been the major problem at that plant, is a failure of their thermal storage system. But on the other hand, Spain's first molten salt plant also had a failure on their thermal storage system. So these are new technologies, and the industry is learning, and so you expect some of these kinds of problems to occur. A lot of focus has been put into trying to identify where the problem here, and I think the next generation of CSP plants, the molten salt tower plants, will solve that particular issue.
Okay, thanks. And do you think that's the everyone should use the system advisory model optimized from NREL before to design, you know, the project, the plant?
So the NREL system advisor model is a good model for trying to look at a lot of options and evaluate different kind of configurations. I think when I talk about issues with the models, it's sort of the next level of detail where you are actually making sure you model the processes in the operation of the plant. So you accurately model the startup, the transient kind of operation. And, you know, the industry had used hourly simulation models at many plants to estimate performance, and that really isn't modeling the accurately the transient kind of operation and performance you'll actually see. And so you got into situations, the Ivanpah projects in the United States had underestimated the transient operation of clouds. And, you know, they used hourly simulation tool to start with, and you don't see the clouds, the transient conditions. But in the case of a steam tower technology, that's really important, and it affects the performance a lot. And that the same is true with many of the trough plants. You know, you see that they used hourly tools, and that's just not adequate. So we need better tools. We need a lot more tools and a lot more analysis done to fully understand. And the tool Bill is working on is really a valuable tool at a little bit higher level.
Thank you. Just the last question to William. Have you ever seen in your modeling reaching a price of the levelized cost of electricity of hybridized systems, CSP, PV, thermal storage, battery storage, reaching 30 megawatt hours, $30 per megawatt hour, sorry?
I haven't seen that specifically. I mean, it's definitely sensitive to what costs you associate with it. All the results that I showed today were assuming the default costs that are in SAM. I'm not a cost modelist, but yeah, if you can get those costs down and you can hit those peak price windows, you can get the PPA price down. But yeah, I have not seen $30 per megawatt hour in my analysis.
Yeah, that would be, you know, the dreaming. So that's why I was asking this. Okay, hopefully in the future. Now we close the electricity and we go to the heat production that produces fuels. So there are some questions, but I want to give you a lot of questions, Christian. So I want to give you first the opportunity to answer to a question that was raised at the session before, and to give a consideration. So about the first about the production of hydrogen through CSP, and the competition through using photovoltaics plus electrolyzers, and also, you know, the transport, the utility of the feasibility to produce in some place hydrogen and ship the hydrogen from like from Japan to Australia. So this is the first consideration. Then there are some other questions that I don't know if we can manage to answer all, but maybe we can answer by email. Thanks.
Exactly. My email address is on the presentation, and everybody can send me emails. Okay, it's a very challenging question, and I can talk for hours on that, but let me give you some simple answers. Producing hydrogen in solar areas will be a major contribution to the future energy system, no matter how it is produced. So if it is a CSP plant plus a PV plant, like William just said, that provides the electricity for operating an electrolyzer 24/7. If it is other plants like high temperature plants that can use the heat not only to produce hydrogen, but also to operate other processes. So, or if it's pure thermochemical cycle, for example, to produce synthesis gas for kerosene production, because we will not get rid of the kerosene in the next decades. It depends very much on the location, how the special situation in the location is. So what is needed in the location and how are the resources? So, and the resource is not only solar, but it's also what is also available. Is there water available? Is there a mineral available where you need a lot of heat? And then I think Luis Crespo said something very wise, that only a small share of the solar plant will be used for the specific process, for example, to produce hydrogen. But you can use the heat very efficiently in the high temperature processes and use part of the heat to produce the hydrogen. However, this will be very much dependent on the market. So what the market asks for is the market is asking for a lot of hydrogen, and there is a chance to provide the hydrogen at a certain cost. It will take it up. And the transportation is only a small share of the cost of the hydrogen in the end. So transporting hydrogen over long distances is possible. So in Europe, we will see that like we do it with natural gas or with power today, that there will be a transfer between Northern Africa and Europe. And we see that power lines are now built between Australia and Asia. And we will see that tankers, that vessels will go between solar locations and the locations where the fuels are needed. And this is especially for countries like Chile or like Australia that are far away from everything, but have excellent resources. So the production will be very cheap compared to other locations, and the transportation will be economical to go from there into the market. So not a simple answer, but yes, there will be opportunities for all the technologies. Nevertheless, the first and large-scale opportunity is electrolysis, especially if you can combine CSP and PV and don't have changing loads on the electrolyzers, then the production of hydrogen should be rather cheap today. But in the future, we will see that other processes will take up the heat and will provide part of the heat for the hydrogen production that is then also cheap. As I mentioned, the solar heat is not so expensive as the solar power. So if you use the heat directly for the chemical process, you have a benefit in using it. Yeah. Simple answer. Good.
Okay, just about that, just to the cost of the heat that you put in your presentation of from a concentrated solar thermal technology is less than €1 per kilowatt hour, I think, thermal.
Yes.
Yeah, is that correct? Because it's a little
what
cheap.
my CSP colleague told me.
Okay.
I didn't do. Hank is nodding, so he must know it best. It's about right, Hank, is it?
Is
Yeah.
that right? Okay, it's good. Thank you very much. I thought that was higher. So I have the other question from, sorry for the pronounce, I'm Ross, I don't know. So just for you, Christian. So Seria is the benchmark material to split water by the solar thermochemical cycle. The reduction of Seria is a bottleneck. Efficiency of the solar water splitting process is low. Can you please comment on it? Are there any other material with higher hydrogen yield to allow this technology to enter into the market? Thanks.
Well, splitting water is always a tricky reaction, and you can use this metal oxide cycles like with Seria. You could use other processes. I presented the sulfur process. you have other problems there with the corrosive sulfuric acid. However, the temperature is much lower, so it's possible to go to sulfur again, especially if it is a part of your production anyway. And then there is a lot of work going on presently to find substances that can be more efficient than ceria, so reduce the reduction temperature, increase the amount of oxygen that can be taken up. So there is development going on, and it's work that's done by my colleagues. It's done all over the world in the labs, and we are looking forward to getting more good materials that will have better reactivity and than we have with ceria. And actually, coming from a time where PV was not competitive to anything, I'm pretty sure that the colleagues who do the material development will find a way to improve the possibilities that we have in these thermochemical reactions. And therefore, it's a good time now to look in the materials to see where we can go with them. And the possibilities are definitely there.
There is another question for the hydrogen economy. So they ask, is the global availability of platinum a big constraint for the full deployment of hydrogen economy?
Actually, it's a major development to reduce the amount of platinum in all these electrolyzers and fuel cells. So for the technologies, I would say no. Because there are alternatives, and I mean, we could see, especially in fuel cells, how much the amount of platinum is reduced. So it should be feasible to do so. And there are different technologies for electrolyzers, and especially when you go to large scale and don't want to have fluctuating load, you can go to systems where platinum shouldn't be an issue.
Okay, thanks a lot. I think it's 32, so we run up with the time. I really want to thank you all for the contribution, for the attention, for the answering the question. Hopefully that if you receive other questions, you can answer it through the email. And that's it. Maybe we will give the floor to Manuel, or say all the audience. See you tomorrow morning. Manuel, the floor is yours.
Yes, see you tomorrow morning. Thank you very much. Has been an excellent session, and I think in general have been an excellent day. And I'm very happy of how things are going. I hope that you are also. And thank you very much for all your contribution, and thank you to the audience to be with us. Thank you. See you tomorrow.
Thank you, Manuel. Bye-bye.